The epoch of reionization, a pivotal and deeply fascinating chapter in the grand narrative of our cosmos, unfolded in the universe's youth. Roughly between 400 million and 1 billion years after the Big Bang. This was a time of profound transformation, a cosmic dawn that marked the end of the universe's long, dark childhood. During this era, the very first stars and galaxies began to flicker into existence, their intense, nascent ultraviolet light acting as a cosmic catalyst, ionizing the vast, neutral hydrogen gas that had permeated the cosmos since the time of recombination. This process was, in essence, a grand awakening. It turned the universe from a dark, opaque, and featureless state into a transparent, luminous, and structured one, allowing light to travel freely across vast cosmic distances for the very first time. It is for this reason that the epoch of reionization is so vital to our understanding of the evolution of the cosmos. It is the moment when the lights came on. Scientists now understand that this grand transformation was not a simple, uniform event, like a single light switch being flicked. Instead, it was a complex, patchy, and protracted process. Different regions of the universe underwent this reionization at different rates, their progress dictated by the local density of matter and the clustering of the first nascent cosmic structures. One of the central questions that drives the research into this era is the precise duration of the epoch. Our current estimates suggest that it spanned several hundred million years, but the exact timeline remains a subject of intense debate and investigation, a puzzle whose pieces are scattered across the vast expanse of cosmic time, hidden in the faint, ancient light from the universe's dawn. Another key area of inquiry is the role played by the first generation of cosmic behemoths, the first massive stars, and the first supermassive black holes. These two entities are thought to have been the primary engines of reionization, their prodigious output of high-energy radiation acting as the cosmic blowtorch that burned away the neutral hydrogen fog. The very first galaxies, which were born in this turbulent and transformative era, were likely very different from the grand, spiral, and elliptical galaxies we see today. They were probably smaller, more clumpy, and more irregular, with chaotic, furious bursts of star formation, their structures still in the process of being assembled. To peer back in time and study this ancient epoch, astronomers have developed a range of ingenious, indirect techniques. One of the most powerful of these is the analysis of the light from distant quasars, the incredibly luminous and active cores of the most distant galaxies. As the light from a quasar travels towards us across billions of light years, it passes through the vast, intervening clouds of the intergalactic medium. The neutral hydrogen atoms in these clouds absorb the quasar's light at a specific, characteristic wavelength, creating a dense thicket of absorption lines in the quasar spectrum, a phenomenon known as the Lyman-alpha forest. By studying the pattern and density of this forest, astronomers can deduce the amount of neutral hydrogen present at different times in the universe's history, effectively creating a core sample of the cosmic past and tracing the progress of reionization. But our most powerful tools for this cosmic archaeology are our great observatories. The Hubble Space Telescope has given us our first tantalizing glimpses of the galaxies that lived in this era, and its successor, the James Webb Space Telescope, with its unparalleled infrared sensitivity, is designed to push this frontier back even further, to capture the faint, red-shifted light of the very first stars and galaxies themselves. The story of reionization is also a story of feedback. The very processes that drove the reionization, the intense radiation from young stars, the powerful winds they blew, the cataclysmic explosions of supernovae also had a profound impact on their surroundings. This feedback could both help and hinder the process of galaxy formation, either by compressing gas to trigger new star birth or by heating it up and blowing it away, quenching star formation altogether. This complex, delicate dance between creation and destruction, between the galaxies and their environment, is a central theme in modern astrophysics, and it is a dance whose choreography was first established during the epoch of reionization. To unravel this intricate interplay, scientists rely on sophisticated computer simulations, vast digital universes in a box, where they can model the growth of cosmic structures, the birth of stars, and the spread of ionizing radiation, and then compare their virtual cosmos with the one we observe. The epoch of reionization, often abbreviated as EOR, is more than just a historical curiosity. It is a fundamental turning point in the story of our universe, a bridge between the simple, smooth, and dark cosmos of the beginning and the complex, structured, and luminous universe we inhabit today. Occurring roughly between 400 million and 1 billion years after the Big Bang. This was the era when the universe, for the second time in its history, became ionized. The first time was in the hot, dense plasma of the Big Bang itself. But after the universe expanded and cooled for 380,000 years, the protons and electrons combined to form neutral hydrogen atoms, ushering in the cosmic dark ages. The EOR marks the end of these dark ages. The light from the very first stars and galaxies began to flood the cosmos, and this high-energy, ultraviolet light had enough power to strip the electrons from the neutral hydrogen atoms once again, creating a hot, ionized plasma of free electrons and protons. This transition from a neutral to an ionized state had profound consequences. It made the universe transparent. In the neutral, dark ages, any visible light emitted by a hypothetical source would have been quickly absorbed by the surrounding hydrogen gas. But in the ionized universe, light could travel freely across vast cosmic distances. This is the reason we can see the distant galaxies today. The EOR, in a very real sense, is the event that made observational cosmology possible. The significance of this epoch extends far beyond the simple act of illumination. The very processes that drove the reionization, the birth of the first stars, the growth of the first galaxies, the feedback of energy and radiation into the intergalactic medium are the same processes that shape the large-scale structure of the universe. The energy pumped into the intergalactic medium by the first luminous objects heated up the gas, affecting the way it would later collapse to form new generations of stars and galaxies. This feedback loop between the first objects and their environment is a key, and still poorly understood, aspect of galaxy formation. By studying the EOR, we can learn about the properties of these first luminous objects. We can infer their masses, their temperatures, their lifetimes, and the types of heavy elements they forged in their nuclear furnaces. These first stars, the so-called population 3 stars, are thought to have been very different from the stars we see today, much more massive, much hotter, and made of almost pure hydrogen and helium. Their explosive deaths as supernovae provided the first chemical enrichment of the universe, seeding the cosmos with the carbon, oxygen, and other heavy elements that are essential for the formation of planets and, ultimately, for life as we know it. The study of the EOR is an ongoing and rapidly advancing frontier of modern astronomy, with a new generation of powerful telescopes, like the James Webb Space Telescope and the Square Kilometre Array. We are, for the first time, beginning to have the tools to probe this ancient era directly. We are moving from a picture based on theoretical models and indirect inferences to one based on direct observational data. The EOR is not just a milestone in the history of the universe. It is a key that has the potential to unlock some of the deepest mysteries of cosmic evolution. From the nature of the first stars to the formation of the cosmic web of galaxies that makes up our cosmic home. The epoch of reionization, That pivotal period in the universe's history between roughly 400 million and 1 billion years after the Big Bang marks the grand transition from a dark, opaque cosmos to a luminous, transparent one. The story of this epoch is written in the faint, ancient light from the first stars and galaxies. And by studying this light, we are beginning to piece together a timeline of this cosmic dawn. The Cosmic Dark Ages, the period of darkness that preceded the EOR, began about 380,000 years after the Big Bang. At the time of recombination, for the next several hundred million years, the universe was a quiet, dark, and largely featureless place, filled with a uniform fog of neutral hydrogen gas, but it was not completely static. In this primordial darkness, the seeds of all future structure were slowly beginning to grow. Tiny quantum fluctuations from the period of cosmic inflation had been stretched to macroscopic scales, creating regions of slightly higher and slightly lower density. Under the relentless pull of gravity, the denser regions began to attract more and more matter, slowly collapsing to form the first gravitationally bound halos of dark matter and primordial gas. The formation of the first stars and galaxies within these halos marks the end of the Dark Ages and the beginning of the epoch of reionization. Our current best estimates, based on a combination of theoretical models and observations of the most distant known galaxies and quasars, suggest that this process began in earnest around 400 million years after the Big Bang. The peak of this activity, the time when the universe was being reionized most rapidly, is thought to have occurred around 750 million years after the Big Bang. By about 1 billion years after the Big Bang, the process was largely complete. The individual, expanding bubbles of ionized hydrogen created by the first stars and galaxies had overlapped and merged, and the vast majority of the hydrogen in the intergalactic medium was in a hot ionized state. The fog had lifted, and the universe had entered its modern, transparent phase. This timeline, however, is still a subject of active research and refinement. Telescopes like the Hubble Space Telescope have been instrumental in pushing our observational frontier back into this era, but they are at the very limit of their capabilities. The James Webb Space Telescope, with its much larger mirror and its optimization for infrared light, is designed to revolutionize our study of this epoch. It will be able to detect the faint, red-shifted light from even earlier and smaller galaxies, allowing us to map out the progress of reionization with unprecedented detail. The story of reionization is not just a story about light and hydrogen, it is a story that is intimately connected to the great unsolved mysteries of modern cosmology. The nature of dark matter and dark energy. Dark matter provided the invisible gravitational scaffolding upon which the first stars and galaxies formed. Without it, the process would have been far too slow to account for the observed timeline of reionization. Dark energy, the mysterious force that is now accelerating the expansion of the universe, also played a role, albeit a more subtle one, in this early epoch. The overall expansion rate of the universe, which is governed by the interplay of dark matter, dark energy, and normal matter, set the cosmic clock, determining the timescale over which structures could form and reionization could proceed. The epoch of reionization is a fascinating and complex chapter in our cosmic story, a chapter that is still being written. It is a story of how, from a dark, simple, and featureless beginning, the universe was transformed into the vast, dynamic, and beautiful cosmos we see today. A cosmos filled with billions of galaxies, trillions of stars, and at least one planet where a curious, intelligent species is just beginning to piece together the story of its own cosmic origins. Before the epoch of reionization, in the long, quiet period known as the Cosmic Dark Ages, the universe was a place of profound simplicity and darkness. This era, which stretched from about 380,000 years after the Big Bang to the ignition of the first stars some 400 million years later, was a time before light, before structure, before the complexity we now take for granted. After the hot, dense plasma of the Big Bang had cooled enough for protons and electrons to combine into neutral hydrogen atoms, the universe became transparent to the relic radiation of its own birth. This radiation, which we now observe as the cosmic microwave background, streamed freely through the cosmos, but there were no new sources of light to replace it. The universe was a vast, expanding, and cooling fog of neutral hydrogen and helium gas, suffused with a faint, ever-dimming afterglow. The matter in this early universe was remarkably smooth and uniform, a consequence of the smoothing effect of cosmic inflation, but it was not perfectly uniform. Tiny, quantum fluctuations from the very first moments of the universe's existence had been stretched to macroscopic scales, creating subtle variations in density from place to place. These tiny seeds of structure, differences of just 1 part in 100,000, were the only interesting feature in an otherwise featureless cosmos. But they were enough. In this dark and quiet universe, gravity was the only force at play on large scales, and it was a patient and relentless sculptor. The regions of slightly higher density exerted a slightly stronger gravitational pull, and they began to slowly, inexorably attract the matter from the surrounding, less dense regions. This is a process of runaway growth. The richer get richer. As a dense region pulls in more matter, its gravitational pull becomes even stronger, and it pulls in even more matter. Over hundreds of millions of years, this slow gravitational collapse began to form the first gravitationally bound structures, vast spherical halos of dark matter, the invisible, mysterious substance that makes up the vast majority of the matter in the universe. The primordial gas of hydrogen and helium was pulled along for the ride, falling into the deep, gravitational wells created by these dark matter halos. As the gas in the center of these halos became denser and denser, it began to cool, radiating away its heat. Eventually, in the very densest cores of the most massive of these first halos, the gas became dense enough and cool enough to fragment and collapse under its own gravity, giving birth to the very first stars. The ignition of these first stars, the so-called population 3 stars, marks the end of the cosmic dark ages. Their fierce, brilliant light, the first light the universe had seen since the Big Bang itself, began to flood the cosmos, and the epoch of reionization had begun. This transition from a dark, featureless, and simple universe to a luminous, structured, and complex one is one of the most profound and important in all of cosmic history. It is the story of how, from a state of near-perfect simplicity, all the rich and wonderful complexity of our modern universe, the galaxies, the stars, the planets, and ourselves, was born. The Dark Ages were not a time of nothingness. They were a time of quiet, patient, and pregnant waiting. A time when the universe was gathering its strength, preparing the ground for the great, creative explosion of light and life that was to come. The end of the cosmic dark ages and the beginning of the epoch of reionization is a story of a universe in transition, a story of the first light in a long, dark night. The Dark Ages, as we have seen, began about 380,000 years after the Big Bang, when the universe became transparent and the cosmic microwave background was released. For the next several hundred million years, the universe was a dark, quiet, and largely featureless place. But this quiet was not destined to last. The relentless work of gravity was slowly, patiently, assembling the first structures from the primordial soup of dark matter and primordial gas. The end of the Dark Ages is not a single, sharp event in time, but a gradual, dawning process. It is the moment when the first stars and galaxies begin to form and to emit light, the moment when the universe begins to be reionized. Our current best estimates, based on a combination of theoretical models and observational data, place the beginning of this epoch at around 400 million years after the Big Bang. It is at this time that the densest regions of the universe had collapsed enough to form the first, massive, and brilliantly luminous population 3 stars. The intense, high-energy, ultraviolet radiation from these first stars was the key to ending the darkness. This radiation was powerful enough to strip the electrons from the surrounding neutral hydrogen atoms, creating expanding bubbles of hot, ionized gas. As more and more stars and galaxies formed, these ionized bubbles grew larger and larger, eventually overlapping and merging until the entire intergalactic medium was transformed from a cold, neutral fog into a hot, ionized plasma. The universe had become transparent once again, not because it was in thermal equilibrium as it was in the very beginning, but because the hydrogen atoms that had once absorbed the light had been torn apart by the fierce radiation of the first stars. This process of reionization was not a quick one. It is thought to have taken several 100 million years to complete. The universe was likely reionized in a patchy, inhomogeneous way, with the densest regions, which formed stars first, becoming ionized earlier than the less dense, void regions. By about 1 billion years after the Big Bang, the process was essentially complete, and the universe had entered its modern, luminous, and transparent phase. The end of the Dark Ages is not just a transition from darkness to light, it is a pivotal moment in the chemical and structural evolution of the cosmos. The first stars, through their nuclear fusion processes and their final explosive deaths as supernovae, forged the first heavy elements, the metals that are essential for the formation of rocky planets and for the chemistry of life. They pumped a tremendous amount of energy and momentum into their surroundings, heating the intergalactic medium and triggering new generations of star formation. They are the true ancestors of all that we see today. The story of the end of the Dark Ages is a story that is being written right now by a new generation of powerful telescopes. The James Webb Space Telescope, with its ability to see the faint, red-shifted light from the very first galaxies, is a machine that is purpose-built to explore this cosmic dawn. By studying the light from these distant, ancient objects, we are, for the first time, beginning to piece together the detailed timeline of this grand cosmic transformation, to understand how, from a long, dark, and silent night, the beautiful, complex, and luminous universe we inhabit was finally born. The first stars to ignite in the universe, the so-called population 3 stars, were the true pioneers of the cosmos, the lonely beacons that first pierced the darkness of the cosmic Dark Ages. They were, in every sense, a different breed from the stars we see today, formed from the pristine, primordial gas of the early universe, which was composed almost entirely of hydrogen and helium. These stars were metal-free. This lack of heavy elements had a profound impact on their formation and their properties. In the modern universe, heavy elements like carbon and oxygen act as efficient coolants, allowing gas clouds to radiate away their heat and to fragment into many small, dense cores, which then collapse to form a wide range of stars, from massive blue giants to small, long-lived red dwarfs like our Sun. But in the metal-free gas of the early universe, this cooling process was much less efficient. The only available coolant was molecular hydrogen, which is far less effective than heavy elements. As a result, the first gas clouds could not fragment as easily. They tended to collapse monolithically, forming single, incredibly massive stars. Our best theoretical models suggest that the first stars were true behemoths, with masses ranging from several tens to perhaps even hundreds of times the mass of our Sun. These massive, metal-free stars would have been incredibly hot, incredibly luminous, and incredibly short-lived. A star 100 times the mass of the Sun would have a surface temperature of over 100,000 Kelvin, It would shine with a luminosity over 1,000,000 times that of the Sun, and it would burn through its nuclear fuel in just a few million years. A mere blink of an eye on cosmic timescales. The intense, high-energy ultraviolet radiation from these first stars was the primary engine of the epoch of reionization. A single, massive population 3 star could ionize a vast bubble of the surrounding hydrogen gas, creating the first pockets of transparency in the primordial fog. But the legacy of these first stars extends far beyond their role in reionization. They were the first chemical factories in the universe. In their incredibly hot and dense cores, they forged the first heavy elements through the process of nuclear fusion. At the end of their short, spectacular lives, these massive stars would have exploded as powerful supernovae, or in some cases, even more energetic pair-instability supernovae or hypernovae. These explosions would have scattered the newly forged heavy elements, the carbon, the oxygen, the silicon, the iron, into the surrounding intergalactic medium. This was the first chemical enrichment of the universe. This metal-rich ejecta would then be incorporated into the next generation of gas clouds, which could then cool more efficiently, fragment more easily, and form a new generation of stars, the population 2 stars, which would be smaller, longer-lived, and would have a small, but non-zero, metallicity. This is a process that has continued for billions of years, with each generation of stars enriching the interstellar medium with more heavy elements, leading eventually to the metal-rich population 1 stars, like our Sun, that we see today. The first stars, the population 3 stars, have long since died. They are too distant and too faint for us to observe directly, even with our most powerful telescopes. But we can search for their fossil record. We can look for the unique chemical fingerprint they would have left on the oldest, most metal-poor stars in our own Milky Way galaxy. And we can use telescopes like the James Webb Space Telescope to look for the collective glow of the first galaxies, the galaxies that were powered by these first, brilliant and transformative stellar pioneers. The first stars are the missing link in our story of cosmic evolution, the bridge between the simple, primordial universe of the Big Bang and the rich, complex, and life-bearing universe we inhabit today. They are our ultimate cosmic ancestors, and the quest to understand them is a quest to understand our own deepest origins. The formation of the very first galaxies, which began in earnest some 400 million years after the Big Bang, was a crucial and transformative event in the history of the cosmos. These were the crucibles in which the first stars were born, the engines that drove the epoch of reionization, and the building blocks from which all the larger, more complex galaxies we see today were eventually assembled. The story of their formation is a story of gravity, of gas, and of the mysterious, invisible scaffolding of dark matter. In the early universe, as we have seen, gravity began to amplify the tiny primordial density fluctuations, pulling matter together to form the first gravitationally bound halos of dark matter. These halos acted as cosmic cradles, their deep gravitational wells attracting the primordial gas of hydrogen and helium. As this gas fell into the dark matter halos, it was shock-heated to high temperatures. For a galaxy to form, this gas had to be able to cool and condense, to sink to the center of the halo, and to become dense enough to form stars. The efficiency of this cooling process was a critical factor in determining when and where the first galaxies formed. In the most massive halos, the gas was so hot that it could not cool effectively, and star formation was suppressed. But in the smaller, mini-halos, with masses of about 1,000,000 times that of the Sun, the gas could cool via the emission of radiation from molecular hydrogen, allowing it to collapse and to form the very first Population 3 stars, these first stellar systems, perhaps containing just a few incredibly massive stars, were the first proto-galaxies. But the story did not end there. The intense radiation from these first stars and their eventual deaths as supernovae had a profound feedback effect on their surroundings. The radiation could heat up the gas in the surrounding halo, preventing it from cooling and forming more stars. The supernova explosions could blow the gas out of the small mini-halos altogether, quenching star formation in that region. This negative feedback meant that the first galaxies were likely to have been small, inefficient, and short-lived. But this was not just a story of destruction. It was also a story of creation. The supernovae from the first stars enriched the surrounding gas with the first heavy elements. This metal-enriched gas could then cool much more efficiently, allowing for a new, more vigorous, and more sustained burst of star formation in the next generation of slightly more massive dark matter halos. This is the beginning of the hierarchical process of galaxy formation. The small, first galaxies, the dwarf galaxies, would have been the most numerous. Over cosmic time, these small galaxies would have merged and collided, their mutual gravitational attraction pulling them together to form larger and larger galaxies. This process of mergers and acquisitions is the primary way in which massive galaxies, like our own Milky Way, are thought to have been built. The epoch of reionization was a time when this hierarchical assembly process was in full swing. The universe was a chaotic and violent place, with small galaxies constantly crashing into each other, triggering spectacular bursts of star formation, and their collective light working to ionize the surrounding intergalactic medium. The first galaxies were not just passive collections of stars, they were active, dynamic, and transformative engines that fundamentally reshaped their cosmic environment. They were the agents that ended the cosmic dark ages, that chemically enriched the universe, and that laid the foundations for the grand cosmic web of galaxies that we see today. Studying these first, faint, and distant objects is one of the primary scientific goals of the James Webb Space Telescope, and its initial findings are already challenging our simple models and revealing a story that is far richer, more complex, and more surprising than we ever imagined. The light that floods our universe, the radiation that allows us to see the distant stars and to trace the history of the cosmos, comes in a vast spectrum of different colors, or wavelengths. And the type of radiation that was most important during the epoch of reionization was the high-energy, ultraviolet light. But the first stars and galaxies were not the only sources of energetic radiation in the early universe. There were also the first quasars, the first active galactic nuclei, powered by the first supermassive black holes. The story of how these first black holes formed is another of the great unsolved puzzles of modern astrophysics. One possibility is that they were the remnants of the very first population 3 stars. The most massive of these stars, those with masses greater than about 250 times that of the Sun, would not have exploded as supernovae at the end of their lives. Instead, they would have collapsed directly to form black holes, with masses of about 100 times that of the Sun. These seed black holes could then have grown over cosmic time by accreting gas from their surroundings and by merging with other black holes, another, more exotic possibility is direct collapse in certain specific conditions in the early universe. A vast cloud of primordial gas, with a mass of about 100,000 times that of the Sun, could have collapsed directly to form a massive black hole, bypassing the intermediate stage of star formation altogether. Whatever their origin, we know from observations of the most distant quasars that supermassive black holes, with masses of over 1 billion times that of the Sun, were already in place in the centers of galaxies by the time the universe was less than 1 billion years old. This is an incredibly short timescale for them to have grown so large, and it presents a major challenge to our theoretical models. But however they formed, these first actively growing black holes would have been prodigious sources of high-energy radiation. As gas spirals into a black hole, it forms a hot, dense accretion disk. The friction and the intense gravitational forces in this disk heat the gas to millions of degrees, causing it to shine with an incredible luminosity, often outshining the entire host galaxy. This radiation is emitted across the entire electromagnetic spectrum, from radio waves to gamma rays, but a significant fraction of it is in the form of high-energy ultraviolet photons and X-rays. This radiation would have been a powerful, and perhaps even dominant, source of ionization during the later stages of the epoch of reionization. The X-rays, in particular, would have had a different effect from the UV photons from stars. They are more penetrating, and they could have heated the intergalactic medium over much larger distances, preheating the gas and making it easier for the later UV photons to ionize it. The interplay between the radiation from the first stars and the radiation from the first quasars is a key, and still poorly understood, aspect of the reionization story. It is a story of two different kinds of light, two different kinds of cosmic engine, working together, and sometimes in opposition, to transform the universe from a dark, neutral fog into the transparent, ionized cosmos we inhabit today. The James Webb Space Telescope, with its ability to see both the faint, starlight from the first galaxies and the powerful, energetic light from the first quasars, is the perfect tool for unraveling this complex and beautifully intertwined story of the first light. The red shift at which the epoch of reionization began and ended is one of the key observational parameters that cosmologists are trying to pin down. Redshift is the astronomical measure of how much the light from a distant object has been stretched by the expansion of the universe. A higher redshift corresponds to an earlier time in cosmic history. The epoch of reionization is thought to have taken place over a range of redshifts, from about a redshift of 12 to a redshift of 6. This corresponds to a period in the universe's history from about 300 million years to 1 billion years after the Big Bang. Pinpointing the precise start and end of this epoch is a challenging observational task. One of the primary tools we use is the cosmic microwave background. As the photons from the CMB travel towards us from the time of recombination, they can be scattered by the free electrons that were liberated during the epoch of reionization. This scattering leaves a subtle imprint on the polarization of the CMB, a signal that can be measured by sensitive experiments like the Planck satellite. The total amount of this scattering, a quantity known as the optical depth to reionization, gives us an integrated measure of the total number of free electrons along the line of sight, and therefore an estimate of the average redshift at which reionization occurred. The latest measurements from Planck suggest an average redshift of about 7.7, which corresponds to a time of about 660 million years after the Big Bang. But this is just an average. To trace the detailed history of reionization, we need to use a different probe, the Lyman-alpha forest. As we have seen, this is the pattern of absorption lines that is imprinted on the spectrum of a distant quasar by the intervening clouds of neutral hydrogen. In the modern, highly ionized universe, the Lyman-alpha forest is a sparse forest of narrow absorption lines, corresponding to the small, residual pockets of neutral gas that exist in the intergalactic medium. But as we look back in time, to higher and higher redshifts into the epoch of reionization, this forest becomes thicker and thicker. The absorption lines begin to merge, and eventually, at a redshift of around 6, we see a Gunn-Peterson trough, a region of complete absorption, which tells us that the universe at that time was still significantly neutral. The disappearance of this trough as we look to lower redshifts is a direct signal of the end of reionization. Finding the beginning of reionization is even more challenging. It requires us to find the very first, and therefore most distant, and therefore faintest galaxies. The Hubble Space Telescope has been able to find galaxies out to a redshift of about 11, which corresponds to a time of about 400 million years after the Big Bang. These galaxies are seen to be driving bubbles of ionization around them, but the universe as a whole at that time was still mostly neutral. The James Webb Space Telescope is designed to push this frontier even further, to find galaxies at redshifts of 15, 20, or even higher, and to directly witness the very first moments of the cosmic dawn. By combining all of these different observational probes, the polarization of the CMB, the Lyman-alpha forest in quasar spectra, and the direct detection of the first galaxies, we are beginning to piece together a coherent and detailed picture of this crucial and transformative era in our cosmic history. It is a story that is being written, redshift by redshift, in the faint, ancient light from the edge of the observable universe. The quest to understand the epoch of reionization is a detective story of cosmic proportions, and astronomers are using a wide array of observational techniques to gather the clues. Deep field imaging with space telescopes like Hubble and Webb is one of the most powerful of these. By staring at a single, small patch of the sky for hundreds of hours, these telescopes can collect enough light to reveal the faint, distant galaxies that lived during the EOR. The color of these distant galaxies, which is determined by their redshift, allows us to place them on a cosmic timeline, spectroscopy. The technique of breaking down the light from an object into its constituent colors is another crucial tool. The spectrum of a distant galaxy can tell us about its chemical composition, its star formation rate, and its redshift. The spectrum of a distant quasar, as we have seen, can be used to probe the state of the intergalactic medium through the Lyman-alpha forest. But perhaps the most promising and also most challenging technique for studying the EOR is 21-centimeter radioastronomy, neutral hydrogen atoms, which fill the universe during the Dark Ages, and the EOR can emit and absorb radio waves at a very specific wavelength of 21 centimeters. This 21-centimeter line is a very faint signal, but it has a huge advantage. It can be seen from the neutral gas itself, not just from the luminous sources within it, in principle. By mapping the intensity of this 21-centimeter signal across the sky and at different frequencies, we could create a full three-dimensional map of the distribution of neutral hydrogen throughout the entire epoch of reionization. This would be a truly revolutionary achievement. We would be able to directly see the bubbles of ionized gas growing and merging around the first galaxies. We would be able to measure the size and shape of these bubbles, which would tell us about the properties of the ionizing sources. We would be able to see the cosmic web in its infancy, to trace the filaments of neutral gas that were feeding the first galaxies. This is the holy grail of EOR research. The challenge is that the 21-centimeter signal from the early universe is incredibly faint, and it is swamped by the much brighter radio emission from our own Milky Way galaxy and from other, more nearby radio sources. Separating this faint, cosmological signal from the bright foreground contamination is one of the greatest experimental challenges in modern astronomy. A number of ambitious new radio telescopes, like the Low-Frequency Array in Europe and the Murchison Wide Field Array in Australia, and in the future, the Square Kilometre Array, are specifically designed to meet this challenge. They are using sophisticated signal processing techniques and vast amounts of computing power to try and tease out this faint, ancient whisper from the cosmic noise. The first tentative detections of the global 21-centimeter signal have recently been reported, and while they are still controversial, they are a tantalizing sign of the revolutionary discoveries that are to come. By combining all of these different observational techniques, the deep images from Webb, the spectra from quasars, and the 3D maps from 21-centimeter radio astronomy, we are entering a new era in our exploration of the cosmic dawn. We are moving from a story based on sketches and outlines to one that is being filled in with rich, detailed, and multifaceted observational color. The 21-centimeter hydrogen line is a unique and powerful tool for probing the dark ages and the epoch of reionization, the period in the universe's history from about 380,000 years to 1 billion years after the Big Bang. This faint radio signal is emitted by the spin-flip transition of the electron in a neutral hydrogen atom. The proton and the electron in a hydrogen atom both have a quantum mechanical property called spin, and these spins can be either aligned or anti-aligned. The aligned state has a slightly higher energy than the anti-aligned state. A neutral hydrogen atom in the higher energy, EI, aligned state can spontaneously flip to the lower energy, anti-aligned state, emitting a photon with a very specific wavelength of 21 centimeters. This is a very rare transition. But since there was such a vast amount of neutral hydrogen in the early universe, the collective signal should be, in principle, detectable. By mapping the intensity of this 21-centimeter signal across the sky, astronomers can trace the distribution, the density, and the temperature of the neutral hydrogen gas throughout this crucial, and otherwise dark, period of cosmic history. During the Dark Ages, the 21-centimeter signal would have been seen in absorption against the cosmic microwave background. The primordial gas was slightly colder than the CMB, so it would have absorbed the CMB photons at the 21-centimeter wavelength. A map of the 21-centimeter signal from this era would be a direct picture of the primordial density fluctuations, the seeds of all cosmic structure. Then, as the first stars and galaxies began to form, the story becomes more complex and more interesting. The ultraviolet light from these first luminous objects would have heated up the surrounding gas, causing the 21-centimeter signal to transition from absorption to emission. The gas would have become hotter than the CMB, so it would have emitted 21-centimeter photons. A 3D map of the 21-centimeter signal from this era would show bright, emitting regions around the first galaxies, the first direct evidence of the cosmic dawn. Finally, as the epoch of reionization progressed, the ultraviolet light from the stars and quasars would have ionized the hydrogen gas, stripping the electrons from the protons. Ionized hydrogen does not emit a 21-centimeter signal. So, as the bubbles of ionization grew and merged, the 21-centimeter signal would have gradually disappeared. A map of the 21-centimeter signal from this era would look like a Swiss cheese, with holes of no signal corresponding to the ionized bubbles and the cheese corresponding to the remaining neutral gas. By watching these holes grow and merge over cosmic time, we could create a direct, real-time movie of the process of reionization. This is the immense promise of 21-centimeter cosmology. The challenge, as we have seen, is the faintness of the signal and the overwhelming brightness of the foreground radio emission from our own galaxy. It is like trying to detect the faint hum of a refrigerator in the middle of a rock concert. But with powerful new telescopes and sophisticated data analysis techniques, we are getting closer and closer to being able to make these revolutionary observations. The 21-centimeter hydrogen line is our only direct window into the cosmic dark ages, and it is our most powerful tool for creating a full three-dimensional picture of the epoch of reionization. It is a faint, ancient whisper from the dawn of time, a whisper that has the potential to tell us the complete story of how our universe was transformed from a dark, simple, and featureless place into the luminous, complex, and beautiful cosmos we inhabit today. The cosmic microwave background, the faint relic afterglow of the Big Bang, is the cornerstone of modern cosmology. It is a snapshot of the universe when it was just 380,000 years old. A baby picture that has provided us with a wealth of information about the universe's age, its composition, and its geometry. But the CMB is not just a static picture of the past. It is also a powerful backlit screen against which the subsequent evolution of the universe has been projected. And one of the most important events to have left its imprint on the CMB is the epoch of reionization. As the photons of the CMB have traveled towards us for 13.8 billion years, they have passed through the intergalactic medium. During the epoch of reionization, this medium was transformed from a neutral gas into a hot ionized plasma, a sea of free electrons. These free electrons can interact with the CMB photons, scattering them in a process known as Thomson scattering. This scattering has two main effects on the CMB. First, it smooths out the small-scale temperature fluctuations. The sharp primordial anisotropies that were imprinted on the CMB at the time of recombination are slightly blurred by this subsequent scattering, in the same way that looking at a distant landscape through a frosted glass window would blur the details. The amount of this blurring, which can be measured with high precision by experiments like the Planck satellite, gives us a measure of the total number of scattering events that have occurred along the line of sight, a quantity known as the optical depth to reionization. This optical depth is a powerful, integrated measure of the entire history of reionization. It tells us the total column density of free electrons between us and the last scattering surface, and it allows us to calculate an average redshift, and therefore an average time at which reionization occurred, the second and more subtle effect of reionization on the CMB is on its polarization. The CMB is not just a map of temperature, it is also a map of polarization, a property that describes the orientation of the light waves. The primordial fluctuations in the early universe created a specific pattern of polarization in the CMB, known as E-mode polarization. The scattering of these polarized photons by the free electrons during reionization can generate a new secondary E-mode signal on large angular scales. By measuring the amplitude of this reionization bump in the E-mode polarization power spectrum, we can get another independent constraint on the timing and the duration of the reionization epoch. The CMB, therefore, provides us with a crucial global perspective on the process of reionization. It tells us about the integrated history of the universe's ionization, complementing the more localized and time-specific information that we can get from observations of distant galaxies and quasars. The remarkable consistency between the reionization history inferred from the CMB and the history inferred from these other probes is one of the great triumphs of modern cosmology. It gives us a high degree of confidence that our overall picture of this crucial and transformative era is correct. But the CMB is more than just a passive screen. The tiny primordial temperature and density fluctuations that are visible in the CMB maps are the very seeds from which all the structures in the universe, including the first stars and galaxies that drove the reionization, eventually grew. The CMB tells us about the initial conditions, the raw material, from which the story of reionization began. It is both the beginning and the end of the story, a beautiful, self-consistent loop of cosmic cause and effect. The ionization fraction, the ratio of ionized atoms to the total number of atoms in a given region of space, is the key physical parameter that describes the state of the intergalactic medium and the progress of the epoch of reionization. The story of the universe's ionization history is a story of the evolution of this fraction over cosmic time. In the very early universe, in the hot, dense plasma of the Big Bang, the ionization fraction was essentially 1. All the hydrogen and helium was fully ionized, a sea of free electrons and nuclei. As the universe expanded and cooled, it reached a point about 380,000 years after the Big Bang, where the temperature dropped below about 3,000 Kelvin. At this point, the free electrons were captured by the nuclei to form stable, neutral atoms. This is the process of recombination, and it caused the ionization fraction to plummet to a very low value, close to zero. The universe had become neutral, ushering in the cosmic dark ages. For the next several 100 million years, the ionization fraction remained very low. But then, as the first stars and galaxies began to form, they started to pump high energy, ultraviolet photons, into their surroundings. These photons were capable of ionizing the neutral hydrogen atoms, stripping their electrons once again. This is the process of reionization, and it caused the ionization fraction to start to climb back up. The process of reionization was not a uniform one. The first stars and galaxies formed in the densest regions of the universe, the nodes of the cosmic web. So, reionization would have started in these regions first, creating localized bubbles of ionized hydrogen in an otherwise neutral intergalactic medium. In these bubbles, the ionization fraction was close to 1, while in the surrounding medium, it was close to 0. The story of reionization is the story of how these ionized bubbles grew and merged over time. As more and more stars and galaxies formed, they produced more and more ionizing photons, and the bubbles grew larger and larger. Eventually, they would have started to overlap. This overlap phase is a critical moment in the history of reionization. It is the point at which the ionized regions become a single, connected network that pervades the entire universe, and the neutral regions become the isolated islands. As the overlap phase continued, the universe entered the final stage of reionization. The remaining pockets of neutral hydrogen were gradually mopped up by the ever-increasing flux of ionizing radiation. By about 1 billion years after the Big Bang, at a redshift of about 6, the process was essentially complete. The ionization fraction of the hydrogen in the intergalactic medium was very close to 1 once again, and the universe had entered its modern, transparent, and highly ionized state. Tracing the evolution of this ionization fraction over cosmic time is one of the primary goals of modern cosmology. We do this by using a variety of observational probes. The Lyman-alpha forest in the spectra of distant quasars allows us to directly measure the amount of neutral hydrogen along the line of sight at different redshifts. The polarization of the cosmic microwave background gives us an integrated measure of the total ionization history. And the direct observation of distant galaxies with telescopes like Webb allows us to map the sources of the ionizing radiation and to study the properties of the ionized bubbles around them. By combining all of these different lines of evidence, we are beginning to piece together a detailed and coherent story of the universe's ionization history. A story that is crucial to our understanding of the formation of the first stars, the growth of the first galaxies, and the overall evolution of the beautiful, complex, and luminous cosmos we inhabit. The formation of the first cosmic structures, the first stars, the first galaxies, the first filaments of the cosmic web is a story that is deeply and inextricably linked to the process of reionization. The two are not separate events. They are two sides of the same cosmic coin, a story of co-evolution and feedback that shape the very architecture of our universe. The story begins, as we have seen, with the tiny quantum fluctuations in the primordial universe, the seeds of all structure. Under the influence of gravity, these tiny density variations began to grow. The primary driver of this process was dark matter, the invisible, non-baryonic substance that makes up the vast majority of the matter in the universe. Because dark matter does not interact with light, it was not subject to the radiation pressure that kept the normal baryonic matter smooth and uniform in the early universe. The dark matter could begin to collapse into gravitationally bound halos much earlier than the normal matter. These dark matter halos acted as the gravitational cradles for the first galaxies. The normal matter, the primordial gas of hydrogen and helium, was pulled into the deep gravitational wells of these halos, where it could then cool, condense, and form the first stars. The epoch of reionization is the period when these first luminous structures began to have a profound impact on their environment. The intense ultraviolet radiation from the first stars and quasars heated and ionized the surrounding intergalactic medium. This had a dramatic effect on all subsequent structure formation. In the smallest dark matter halos, this heating could be so intense that it would raise the pressure of the gas, preventing it from collapsing to form new stars. This radiative feedback could effectively quench star formation in the smallest dwarf galaxies, and may be the reason why we observe far fewer small satellite galaxies around the Milky Way than our simplest models of hierarchical structure formation would predict. The process of reionization, therefore, was not just a passive illumination of the universe. It was an active, transformative process that regulated the growth of the very structures that were driving it. The relationship is a complex, nonlinear feedback loop. The first galaxies drove the reionization, and the reionization, in turn, shaped the subsequent evolution of the galaxy population. The reionization process also had a profound impact on the large-scale structure of the universe, the cosmic web. The heating and ionization of the intergalactic medium would have puffed up the gas, smoothing out the smaller-scale density fluctuations and making it more difficult for small galaxies to form in the void regions between the great filaments of the cosmic web. This would have enhanced the contrast of the cosmic web, making the filaments denser and the voids emptier. The large-scale structure we observe today, with its beautiful web-like pattern of galaxies, is a direct legacy of this complex interplay between gravity, dark matter, and the energetic feedback from the first luminous objects during the epoch of reionization. To understand this intricate story, astronomers rely on large-scale cosmological simulations. These are vast, complex computer models that follow the evolution of billions of dark matter particles and gas elements from the early universe to the present day, incorporating the physics of gravity, hydrodynamics, star formation, and radiative feedback. By comparing the results of these simulations with our observational data, from the cosmic microwave background to the distribution of galaxies in the local universe, we can test our theories, refine our models, and piece together the complex and beautifully intertwined story of how the first structures formed and how they forever changed the universe they were born into. The mysterious, invisible substance known as dark matter is the silent, gravitational architect of our universe. It is the unseen scaffolding upon which all the visible structures, the stars, the galaxies, the great cosmic web have been built. While it does not interact with light, and is therefore completely invisible to our telescopes, its gravitational influence is seen everywhere we look. And its role in the story of the epoch of reionization is absolutely crucial. In the early universe, the normal, baryonic matter was tightly coupled to the radiation field. The intense pressure of the photons prevented the baryonic matter from collapsing under gravity to form structures. But dark matter, which does not interact with light, was immune to this radiation pressure. It was free to begin the process of gravitational collapse much earlier. As soon as the universe became matter-dominated, about 50,000 years after the Big Bang, the tiny primordial density fluctuations in the dark matter began to grow. Over the next few 100 million years, this process of hierarchical collapse formed the first gravitationally bound halos of dark matter. These halos were the cosmic cradles, the deep gravitational wells into which the baryonic matter would later fall, once it had decoupled from the radiation at the time of recombination. Without dark matter, The formation of the first stars and galaxies would have been delayed by hundreds of millions or even billions of years. The primordial density fluctuations in the baryonic matter alone were simply too small to have grown into the structures we see by the time of reionization. Dark matter gave the process of structure formation a vital head start. It is the reason that the first stars and galaxies were able to form so early, just a few 100 million years after the Big Bang, and to begin the process of reionizing the universe. The properties of dark matter also had a direct influence on the properties of the first galaxies. The mass, the size, and the distribution of the dark matter halos determined the mass, the size, and the clustering of the galaxies that formed within them. The standard cold dark matter model, which assumes that dark matter is made of slow-moving, weakly interacting particles, has been incredibly successful at explaining the large-scale structure of the universe, but it faces some potential challenges on smaller galactic scales. The cusp core problem, for example, is the observation that the centers of some dwarf galaxies seem to have a lower density of dark matter than the cuspy. High-density profiles predicted by the simplest CDM simulations. The missing satellites problem is the observation that there are far fewer small dwarf satellite galaxies orbiting the Milky Way than the simulations predict. The epoch of reionization may hold the key to solving some of these puzzles. The intense, radiative feedback from the first stars and the reionization itself could have had a profound impact on the distribution of dark matter in the smallest halos. The energetic outflows of gas from the first supernova explosions, for example, could have gravitationally heated the dark matter in the center of a halo, transforming a cusp into a core. The reionization of the intergalactic medium would have heated the gas, making it more difficult for it to be accreted onto the smallest dark matter halos, which could explain why many of them never form stars and remain as dark satellites. The study of the epoch of reionization is therefore not just about understanding the first light. It is also a powerful indirect probe of the nature of dark matter. By comparing the predictions of our simulations, which depend on the properties of dark matter, with our observations of the first galaxies and the process of reionization, we can place powerful constraints on the mass, the interaction cross-section, and the fundamental nature of this mysterious, invisible, and utterly dominant component of our cosmos. The epoch of reionization was a time of many firsts: the first stars, the first galaxies, the first supermassive black holes. And the interplay between these different astrophysical sources is what makes the story of reionization so rich, so complex, and so fascinating. The primary drivers of the reionization are thought to have been the first generation of stars, the massive, hot, and brilliantly luminous population 3 stars. Their intense ultraviolet radiation would have carved out the first expanding bubbles of ionized hydrogen in the primordial neutral fog, but they were not the only players on the cosmic stage. The first, actively growing, supermassive black holes. The engines of the first quasars and active galactic nuclei would also have been prodigious sources of high-energy, ionizing radiation. The radiation from an AGN is different from that of a star. It has a much harder spectrum, with a significant fraction of its energy in the form of X-rays. These X-rays are more penetrating than the UV photons from stars, and they would have had a different and more far-reaching impact on the intergalactic medium. They would have heated the gas over much larger volumes, preheating it and making it easier for the later, softer UV photons from stars to complete the process of ionization. The relative importance of stars versus AGN in driving the reionization is one of the key and still unresolved questions in the field. The answer likely depends on time and environment. In the very earliest stages of reionization, the first small galaxies would have been dominated by star formation. So stars were likely the primary drivers. But as galaxies grew and merged, their central black holes would have grown as well. In the later stages of reionization, the powerful radiation from the most luminous quasars may have become a significant, and perhaps even dominant, contributor to the global ionizing photon budget. Another, more exotic, potential source of ionizing radiation is the decay or annihilation of dark matter particles. If dark matter is made of weakly interacting massive particles, as many models suggest, then these particles could annihilate with each other when they collide, producing a shower of high-energy particles and photons. This dark matter annihilation radiation would have been most intense in the dense dark matter halos where the first galaxies were forming. And it could have provided an early and very widespread source of ionization, potentially helping to kickstart the reionization process even before the first stars had formed. Distinguishing between these different sources of ionizing radiation is a major goal of modern observational cosmology. Each source would leave a different characteristic imprint on the properties of the intergalactic medium and on the statistical properties of the ionized bubbles. By mapping the size and shape of these bubbles using 21-centimeter radio astronomy, and by studying the detailed ionization state of the gas using the Lyman-alpha forest, we can hope to disentangle the contributions of these different astrophysical sources. It is a complex cosmic puzzle with many different pieces, but by combining our theoretical models with the rich, multi-wavelength data from our new generation of telescopes, we are beginning to see how all these different players, the first stars, the first black holes, and perhaps even the dark matter itself, work together to bring about the great luminous transformation of our universe. The process of reionization was not just a one-way street, with the first stars and galaxies passively illuminating their surroundings. It was a dynamic, interactive process, a story of feedback, where the very act of creation had a profound and often complex impact on all subsequent creation. This concept of feedback is one of the most important and also one of the most challenging aspects of modern galaxy formation theory. The feedback from the first stars and galaxies came in several forms. The most direct is radiative feedback. The intense, ultraviolet radiation that ionized the hydrogen gas also heated it up to temperatures of tens of thousands of Kelvin. This heating had a dramatic effect on the ability of the gas to form new stars in the smallest dark matter halos, with masses below about 100 million times that of the Sun. The gravitational pull was not strong enough to hold on to this hot, high-pressure gas. The gas would have been photoevaporated, boiled away into the intergalactic medium, effectively shutting off the fuel supply for any further star formation. This is a powerful form of negative feedback, and it is thought to be the primary reason why the smallest dwarf galaxies are so inefficient at forming stars. Another, more violent, form of feedback is mechanical feedback from supernova explosions. The massive first stars would have ended their short lives in spectacular supernova explosions. These explosions release a tremendous amount of energy and momentum into the surrounding interstellar medium. The expanding shock wave from a supernova can sweep up and eject the gas from a small protogalactic halo, again quenching star formation. But feedback is not always negative. The same supernova shock wave that can destroy a small galaxy can also, in a larger galaxy, compress the surrounding gas, triggering a new burst of star formation. This is a form of positive feedback. The relationship is a complex, nonlinear one, and it depends sensitively on the mass of the galaxy, the density of its gas, and the details of its star formation history. The feedback from the first, actively growing, supermassive black holes would have been even more powerful. The intense radiation and the powerful jets from an active galactic nucleus can heat and eject the gas from an entire galaxy, a process known as AGN feedback. This is thought to be the primary mechanism that regulates the growth of the most massive galaxies in the universe, preventing them from becoming even larger than they are. The process of reionization itself can be seen as the ultimate form of large-scale feedback. The collective radiation from the entire population of the first galaxies transformed the state of the entire intergalactic medium, which in turn had a profound impact on the evolution of all subsequent galaxies. The heating of the IgM during reionization raised the Jeans mass, the minimum mass that a gas cloud needs to be able to collapse under its own gravity. This made it much harder for small galaxies to form after the reionization was complete, effectively suppressing the formation of a new generation of dwarf galaxies. Modeling these complex feedback processes is one of the greatest challenges in modern computational astrophysics. It requires simulations that can span a huge range of physical scales. From the small-scale physics of individual stars and supernovae to the large-scale dynamics of the cosmic web. But it is a challenge we must meet if we are to have a complete and predictive theory of galaxy formation. The story of reionization is a story of a universe that is not just expanding and cooling, but is actively shaping its own destiny. A story where the first light of creation had a profound and lasting impact on all the light and all the life that was to follow. The story of the epoch of reionization is a story that is told in the faint, ancient light from the edge of the observable universe, but it is also a story that is told in the powerful, complex, and beautiful language of mathematics and computer simulation. To unravel the intricate processes that governed this transformative era, astronomers must rely on a close and constant dialogue between observation and theory. Cosmological simulations are our primary theoretical tool for understanding the EOR. These are vast, complex computer models that attempt to recreate a patch of the universe in a virtual box. They start with the initial conditions of the early universe, as measured from the cosmic microwave background, a smooth, uniform distribution of dark matter and gas with tiny, random fluctuations. They then evolve this system forward in time, using the known laws of physics, gravity, hydrodynamics, atomic physics, to track the collapse of dark matter halos, the cooling and accretion of gas, the formation of stars and galaxies, and the propagation of ionizing radiation. These simulations have become incredibly sophisticated. Modern, hydrodynamic simulations can now model the complex physics of gas dynamics, of shock heating, of radiative cooling, of star formation, and of feedback from supernovae and active galactic nuclei, with a high degree of fidelity. They can produce virtual universes that look remarkably like our own, with a realistic cosmic web of galaxies and voids. These simulations are essential for several reasons. First, they allow us to test our theoretical understanding. We can run a simulation with a particular set of physical assumptions, a particular model for star formation, a particular type of dark matter, and then compare the results of the simulation with our observational data. If the simulation does not match the observations, it tells us that our assumptions are wrong, and we need to go back and revise our theory. Second, simulations allow us to explore the vast parameter space of cosmological models. We can change the cosmological parameters, the density of dark matter, the nature of dark energy, the amplitude of the primordial fluctuations, and see how this affects the process of reionization. This allows us to use our observations of the EOR to place powerful constraints on the fundamental properties of our universe. And third, simulations are essential for interpreting our observational data. The signals we observe from the early universe, like the 21-centimeter signal, are incredibly complex, and they are contaminated by a host of foreground and instrumental effects. To extract the cosmological information from these signals, we need to have a detailed, theoretical model of what the signal should look like. Simulations provide this crucial theoretical template. They allow us to create mock observational data, which we can then use to develop and test the sophisticated data analysis pipelines that are needed to analyze the real data from our telescopes. The challenges in modeling the EOR are immense. The range of physical scales involved is enormous, from the sub-parsec scales of individual stars to the gigaparsec scales of the entire observable universe. The physics of star formation and feedback is incredibly complex and still not fully understood. And the computational cost of these simulations is astronomical, often requiring millions of hours of processing time on the world's largest supercomputers. But despite these challenges, the progress has been remarkable. The close synergy between our ever-improving simulations and our ever more powerful observational facilities is what is driving the rapid progress in our understanding of this crucial and fascinating epoch. The simulations are our virtual laboratories, our theoretical test beds, our indispensable guides in the grand human adventure of exploring the cosmic dawn. The story of the universe's ionization history. The journey from the hot, ionized plasma of the Big Bang to the cool, neutral fog of the Dark Ages, and then back to the hot, ionized plasma of the modern universe, is a story that is intimately tied to the fundamental cosmological parameters that govern our cosmos. Different cosmological models with different values for these parameters predict a different ionization history and a different timeline for the epoch of reionization. The standard model of cosmology, the lambda CDM model, has been incredibly successful at explaining a vast range of observational data, from the cosmic microwave background to the large-scale distribution of galaxies. This model is defined by just 6 key parameters, which describe the density of dark matter, the density of baryonic matter, the density of dark energy, the age of the universe, and the properties of the primordial density fluctuations. The values of these parameters have been measured with incredible precision by experiments like the Planck satellite. And when we plug these parameters into our simulations of the epoch of reionization, they produce a story that is, for the most part, consistent with our observations. They predict a reionization that starts around a redshift of 12 and ends around a redshift of 6, driven by the light from the first low-mass galaxies. But there are still some tensions, and these tensions may be hinting at the need for a new, more complex cosmological model. For example, some of our measurements of the Hubble constant from the local late-time universe seem to give a slightly higher value than the one inferred from the early time measurements of the CMB. If this Hubble tension is real, and not just a result of some unknown systematic error, it would imply that our standard lambda CDM model is incomplete. A higher expansion rate in the early universe, for example, would mean that structures would have formed earlier, and the reionization could have started sooner. Some alternative cosmological models, which propose new forms of early dark energy or modifications to the nature of dark matter, have been proposed to solve this tension, and these models would predict a different reionization history. The properties of the primordial density fluctuations, which are also a key input to our reionization models, could also be more complex than in the standard picture. The lambda CDM model assumes that these fluctuations are almost perfectly Gaussian, meaning their statistical properties are very simple. But some models of cosmic inflation predict a small amount of non-Gaussianity, which would lead to the earlier formation of rare, massive dark matter halos, and could provide an earlier start to the reionization process. The study of the epoch of reionization is therefore not just about understanding the astrophysics of the first stars and galaxies. It is also a powerful, independent probe of fundamental cosmology. By comparing the predictions of different cosmological models with our increasingly precise observational data on the reionization history, we can test our fundamental understanding of the universe and search for the subtle, but profound, signatures of new physics beyond the standard model. The faint, ancient light from the cosmic dawn is not just a picture of our past. It may also be a window into a deeper and even more mysterious cosmic reality. The study of distant quasars has provided some of our most powerful and direct probes of the epoch of reionization. These are the most luminous, continuously shining objects in the universe, the brilliant beacons of light from actively growing, supermassive black holes in the centers of the most distant galaxies. Their immense brightness allows us to see them from across the entire observable universe. And their light acts as a cosmic flashlight, illuminating the vast, intervening expanse of the intergalactic medium. As the light from a quasar travels towards us, it is absorbed by any neutral hydrogen gas that lies along the line of sight. This absorption occurs at a very specific wavelength in the rest frame of the hydrogen atom, the Lyman-alpha transition. But because the universe is expanding, the light from the quasar is redshifted, and the wavelength of the Lyman-alpha absorption is also redshifted by an amount that depends on the distance, and therefore the age, of the intervening hydrogen cloud. This creates a dense forest of absorption lines in the quasar's spectrum, the Lyman-alpha forest, with each line corresponding to a different cloud of gas at a different redshift. By studying the properties of this forest, astronomers can create a detailed, one-dimensional core sample of the density, the temperature, and the ionization state of the intergalactic medium all the way from the quasar to us. In the relatively nearby modern universe, where the intergalactic medium is highly ionized, the Lyman-alpha forest is a sparse collection of narrow absorption lines corresponding to the small, residual pockets of neutral gas that still exist. But as we look at quasars at higher and higher redshifts, back into the epoch of reionization, the forest becomes thicker and denser. The absorption lines begin to overlap and merge, a sign that the amount of neutral hydrogen is increasing. And finally, at a redshift of around 6, we see a dramatic change. The forest gives way to a Gunn-Peterson trough, a long, continuous region of complete absorption, where all of the quasar's light at wavelengths shorter than the Lyman-alpha line has been absorbed. This is the smoking gun, the definitive signal that the universe at that time was still significantly neutral. The disappearance of this trough as we look to lower redshifts is a direct observational signature of the end of reionization. The search for and the study of the most distant quasars is therefore a major focus of modern observational cosmology. Surveys like the Sloan Digital Sky Survey have been incredibly successful at finding these rare, ancient objects, pushing our quasar frontier back to a redshift of over 7.5, a time when the universe was just 690 million years old. These most distant quasars are providing us with a unique and powerful window into the later stages of reionization. They are allowing us to map the patchiness of the process, to see the large, ionized bubbles that had formed around the quasars themselves, and to place powerful constraints on the timing of the final mopping-up phase of reionization. They are also a profound puzzle in their own right. The fact that supermassive black holes, with masses of over 1 billion times that of the Sun, were already in place so early in the universe's history is a major challenge to our theories of black hole formation and growth. They are a sign that the early universe was a place where things happened much more quickly and much more dramatically than our simple models would have predicted. While quasars are powerful probes of the later stages of reionization, their immense brightness is also a limitation. They are rare objects, and they tend to live in the most massive, and therefore most biased, regions of the early universe. To get a more complete and representative picture of the reionization process, we need to study the more typical, and therefore much fainter, galaxies that were the primary drivers of the cosmic dawn. This is the realm of the Lyman-alpha emitters. These are star-forming galaxies that have a strong emission line in their spectrum at the Lyman-alpha wavelength. This emission is a direct byproduct of the intense, ultraviolet radiation from their young, massive stars. The UV photons ionize the surrounding hydrogen gas within the galaxy, and when these hydrogen atoms recombine, they cascade down through their energy levels, emitting a cascade of photons, including the characteristic Lyman-alpha photon. LAEs are therefore a direct signpost of the very process of star formation that is thought to be driving the reionization. By searching for these faint emission line galaxies at high redshifts, we can begin to map out the distribution of the ionizing sources themselves. The challenge is that the same neutral hydrogen in the intergalactic medium that creates the Lyman-alpha forest in the spectra of quasars can also absorb the Lyman-alpha emission from these distant galaxies. This means that our ability to see an LAE depends not just on its intrinsic brightness, but also on the ionization state of the IGM along the line of sight. If a galaxy is embedded in a large ionized bubble, its Lyman-alpha photons can escape and travel to us unimpeded. But if it is in a still neutral region, its Lyman-alpha emission will be scattered and absorbed, and the galaxy will be invisible to us in the Lyman-alpha line. This is not a bug, it is a feature. The changing statistics of the key LAE population over cosmic time is a powerful probe of the progress of reionization. As we look to higher and higher redshifts back into the heart of the EOR, we see a dramatic drop in the number of detected LAEs. This is a direct, observational signature of the increasing neutrality of the universe. By mapping the clustering of the LAEs that we can see, we can begin to map the size and the topology of the ionized bubbles in which they live. The clustering of LAEs on large scales is a direct measure of the patchiness of the reionization process. The Hubble Space Telescope, with its deep imaging and its spectroscopic capabilities, has been a pioneer in the study of LAEs, pushing our observational frontier out to a redshift of over 7. And the James Webb Space Telescope is poised to revolutionize this field. Its incredible sensitivity will allow it to detect much fainter, and therefore more typical, LAEs at even higher redshifts, giving us our first direct view of the galaxies that were responsible for the first stages of reionization. By combining the study of the absorption of quasar light with the study of the emission of galactic light, we are beginning to build a complete and beautifully complementary picture of this crucial and transformative epoch, a picture that is told in both the shadows and the light of the early universe. The epoch of reionization was not just a story of light and hydrogen, it was a story that fundamentally reshaped the large-scale structure of our universe. The vast, web-like pattern of galaxies and voids that we see in the local cosmos, the cosmic web, is a direct legacy of the complex interplay between gravity, dark matter, and the energetic feedback from the first luminous objects during this transformative era. In the standard picture of hierarchical structure formation, the cosmic web is formed by the gravitational collapse of the primordial density fluctuations. The overdense regions collapse to form the dense nodes and filaments of the web, where galaxies and clusters of galaxies are found, while the underdense regions expand to become the great empty voids. The process of reionization had a profound impact on this process. The intense ultraviolet radiation from the first stars and galaxies heated the gas in the intergalactic medium to tens of thousands of degrees. This heating had a crucial effect on the subsequent formation of galaxies, particularly the smallest ones. A gas cloud can only collapse to form a galaxy if its own self-gravity is strong enough to overcome its internal pressure. By heating the gas, reionization increased its pressure, making it much more difficult for it to collapse. This raised the gene's mass, the minimum mass that a dark matter halo needs to be able to accrete and hold on to gas. After the universe was reionized, dark matter halos with masses below this new, higher gene's mass were no longer able to form galaxies. They remained as dark halos, unable to attract the hot, high-pressure gas of the intergalactic medium. This process of suppression of galaxy formation in small halos is a key prediction of our models of reionization, and it has a number of important, observable consequences. It can help to explain the missing satellites problem. The fact that we see far fewer small dwarf satellite galaxies around the Milky Way than our simplest simulations would predict. Many of these satellites may have formed in halos that were too small to be able to form stars after the universe was reionized. It also means that the population of galaxies we see today is a biased tracer of the underlying distribution of matter. The smallest galaxies are preferentially found in the densest regions of the cosmic web, the regions that were reionized earliest and where the halos were able to grow massive enough to overcome the suppression effect. The voids, on the other hand, which were reionized later and where the halos are typically smaller, should be even emptier of galaxies than we would expect from gravity alone. The epoch of reionization, therefore, acted to enhance the contrast of the cosmic web, making the rich regions richer and the poor regions poorer. It was a process that not only illuminated the universe, but also fundamentally sculpted its large-scale architecture. The detailed study of the distribution of galaxies at different cosmic epochs, a field known as large-scale structure, is a powerful probe of this process. By measuring the clustering of galaxies and the properties of the cosmic voids, we can test our models of reionization and learn about the properties of the first, ionizing sources. This is a major scientific goal of large, new galaxy surveys, like the Dark Energy Spectroscopic Instrument and the Euclid Space Mission. By combining the information from these large-scale structure surveys with the direct observations of the reionization epoch from telescopes like Webb and the 21-centimeter radio arrays, we can build a complete and self-consistent picture of this crucial and transformative era, an era that not only brought light to the cosmos, but also gave it its grand, beautiful, and intricate web-like form. The thermal history of the intergalactic medium, the story of how the vast, diffuse gas between the galaxies has been heated and cooled over cosmic time, is a story that is intimately and inextricably linked to the epoch of reionization. In the very early universe, the IGM was in thermal equilibrium with the cosmic microwave background radiation. But after recombination, when the universe became neutral, the matter and the radiation decoupled. The matter, the primordial gas of hydrogen and helium, then began to cool down as the universe expanded, its temperature dropping faster than the temperature of the CMB. By the time the first stars and galaxies began to form, a few 100 million years later, the IGM was a very cold, dark, and neutral medium, with a temperature of just a few tens of Kelvin. The epoch of reionization dramatically and permanently changed this. The intense, high-energy radiation from the first stars and quasars did more than just ionize the hydrogen. It also injected a tremendous amount of heat into the IGM. The process of photoionization itself is a heating process. When a high-energy UV photon is absorbed by a neutral hydrogen atom, it not only liberates the electron, but it also gives that electron a significant amount of kinetic energy. These energetic photoelectrons then share their energy with the surrounding plasma through collisions, heating the gas up to temperatures of 10 to 20,000 Kelvin. This is a process of photoheating, and it is the primary mechanism by which the IGM was heated during the epoch of reionization. But there may have been other, earlier heating mechanisms as well. The X-rays from the first, actively growing black holes, for example, would have been more penetrating than the UV photons from stars, and they could have heated the IGM over much larger volumes, even before it was fully ionized. The decay or annihilation of dark matter particles is another, more exotic, potential source of early heating. The thermal history of the IGM is therefore a complex story, with different heating mechanisms potentially dominating at different times and in different regions of the universe. After the reionization was complete, the IgM was left in a hot, diffuse, and highly ionized state. Its subsequent thermal evolution was then governed by a competition between two processes, adiabatic cooling due to the expansion of the universe, and continued photoheating from the background flux of ultraviolet radiation from all the quasars and star-forming galaxies in the universe. This balance results in a tight relationship between the temperature and the density of the IgM, an equation of state that has been measured with high precision from the properties of the Lyman-alpha forest. The thermal history of the IgM is a crucial part of our cosmological story. It affects the formation of galaxies, as we have seen by setting the pressure of the gas that is trying to accrete onto dark matter halos. It also affects the properties of the Lyman-alpha forest, which is our primary tool for probing the IgM at high redshifts, and it is a story that is still being written. With new, more precise measurements of the Lyman-alpha forest, and with the direct 21-centimeter observations of the temperature of the neutral gas before and during the reionization, we are beginning to piece together a detailed and beautifully complex picture of the thermal life of our universe, a picture that is crucial to our understanding of the cosmic dawn and the grand, luminous transformation it brought about. The epoch of reionization was not a single, monolithic event, but a complex, multi-phased process that unfolded over several 100 million years of cosmic time. While the details are still a subject of active research, we can broadly divide the EOR into three main phases: the early or pre-overlap phase, the overlap phase, and the late or post-overlap phase. The early phase began with the formation of the very first stars and galaxies in the densest regions of the universe, around a redshift of 15 to 20, or about 200 to 300 million years after the Big Bang. These first luminous objects began to emit ionizing radiation, carving out the first, small, isolated bubbles of ionized hydrogen in the surrounding neutral intergalactic medium. In this phase, the ionized regions were still a tiny fraction of the total volume of the universe. The IgM was, for the most part, still a neutral fog. The overlap phase is the heart of the reionization process. It is the period of rapid, exponential growth of the ionized regions. As more and more stars and galaxies formed, the ionized bubbles grew larger and larger, and they began to merge and overlap with each other. This is a process akin to a percolation transition. At a certain critical point, the ionized regions would have become a single, connected network that pervaded the entire universe, and the neutral regions would have become the isolated islands within this ionized sea. This overlap phase is thought to have occurred over a range of redshifts from about 10 to 7, or from about 470 million to 780 million years after the Big Bang. It was a time of dramatic and rapid change, the time when the universe was being transformed from an opaque to a transparent state. The late phase marks the final mopping up of the remaining neutral hydrogen. After the overlap phase, the vast majority of the volume of the universe was ionized, but there would still have been small, dense, and self-shielded pockets of neutral gas, particularly in the underdense, void regions that had not yet formed many luminous sources. The late phase is the story of how the ever-increasing, and now more uniform, background flux of ionizing radiation from the entire population of galaxies and quasars gradually ate away at these last, stubborn islands of neutrality. This phase is thought to have ended around a redshift of 6, or about 1 billion years after the Big Bang, at which point the ionization fraction of the hydrogen in the IgM was very close to 1, and the universe had entered its modern, highly ionized state. This three-phased story is a simplified one, of course. The reality was likely much more complex, with a rich interplay between different types of ionizing sources, and a complex, inside-out and outside-in topology for the reionization process. But it provides a useful framework for thinking about this crucial and transformative era. And it is a framework that we are now beginning to test with unprecedented detail by combining the power of our largest telescopes, our most sophisticated simulations, and our most ingenious observational techniques in our ongoing quest to create a complete and coherent story of the cosmic dawn. The timing of the epoch of reionization is not just a historical curiosity. It is a crucial parameter that has a profound impact on our interpretation of the observable universe we see today. The precise start and end of this era, and the duration over which it unfolded, affects everything from the properties of the cosmic microwave background to the distribution and evolution of galaxies. The distribution of the galaxies we see in our deep sky surveys, for example, is a direct legacy of the reionization process. As we have seen, the heating of the intergalactic medium during reionization suppressed the formation of small galaxies in the later universe. The timing of this suppression event is therefore crucial for understanding the galaxy luminosity function, the number of galaxies of different brightnesses that we see at different cosmic epochs. A later reionization would have allowed for the formation of more small dwarf galaxies, while an earlier reionization would have quenched their formation more effectively. By comparing the observed number of dwarf galaxies with the predictions of our models, we can place powerful constraints on the timing of the EOR. The cosmic microwave background, our baby picture of the universe, is also a powerful chronometer for reionization. The scattering of the CMB photons by the free electrons liberated during reionization leaves a characteristic imprint on the CMB's polarization, the reionization bump. The amplitude of this bump is a direct measure of the total number of scattering events, and therefore of the total duration and the average redshift of the reionization epoch. The latest high-precision measurements of this bump from the Planck satellite have been instrumental in narrowing down the possible timeline for the EOR and in ruling out models that proposed a very early or a very protracted reionization. The timing of reionization is also intimately linked to the chemical evolution of the universe. The first stars and supernovae, which drove the reionization, also produced the first heavy elements. The timing of this first metal enrichment is a crucial input to our models of all subsequent star and planet formation. An earlier reionization would imply an earlier chemical enrichment, which could have implications for the properties of the oldest stars we see in our own galaxy, and even for the timing of the formation of the first potentially habitable rocky planets. And finally, the timing of reionization is a key input to our understanding of the nature of dark energy. The history of the cosmic expansion rate, which we measure using standard candles like supernovae, depends on the interplay between dark matter, dark energy, and normal matter. The formation of the first structures, and therefore the timing of reionization, is also sensitive to this expansion history. By combining our measurements of the reionization timeline with our measurements of the expansion history, we can perform a powerful, self-consistent test of our entire cosmological model and search for any subtle deviations that could hint at new physics. The timing of reionization is a single, but powerful, piece of the grand cosmic puzzle. And by using a wide array of different complementary observational probes to pin down this crucial date in our cosmic calendar, we are not just learning about a distant, ancient epoch. We are sharpening our understanding of the entire, beautiful, and intricately interconnected story of our cosmic home. The concept of metallicity, the abundance of elements heavier than hydrogen and helium, is one of the most important in all of astrophysics. It is the key to understanding the life cycle of stars, the formation of planets, and the overall chemical evolution of the universe. And it plays a particularly crucial and complex role in the story of the epoch of reionization, the very first stars to form in the universe. The population, the 3 stars, were by definition metal-free. They were forged from the pristine, primordial gas of the Big Bang, a gas that contained only hydrogen and helium. This lack of heavy elements had a profound impact on their properties. Without metals to act as efficient coolants, the first gas clouds could not fragment easily, leading to the formation of incredibly massive stars. These stars, in turn, produced a very hard and very efficient spectrum of ionizing, ultraviolet photons. The first stages of reionization were therefore driven by a very different and much more powerful kind of starlight than what we see in the universe today. But these first stars were also the first chemical factories. At the end of their short, violent lives, they exploded as supernovae, scattering the first heavy elements into the surrounding intergalactic medium. This was the first chemical enrichment of the cosmos. This metal-rich ejecta would then be incorporated into the next generation of gas clouds, and even a tiny amount of metals can have a dramatic effect on the physics of star formation. Metals are incredibly efficient coolants. A gas cloud with even a very low metallicity can radiate away its heat much more effectively than a metal-free cloud. This allows it to cool, to fragment, and to form a new generation of stars, the population 2 stars, which would have been much less massive, on average, than the first. Population 3 stars. This transition from a metal-free population 3 mode of star formation to a metal-enriched population 2 mode is a crucial and still poorly understood event in the history of the early universe. It would have had a profound impact on the process of reionization. The less massive population 2 stars would have produced a softer and less efficient spectrum of ionizing photons than their population 3 predecessors. The transition from POP3 to POP2 star formation would therefore have led to a change in the ionizing efficiency of the galaxy population, a change that would have affected the overall timeline and morphology of the reionization process. Metallicity also has a direct impact on the feedback processes that regulate galaxy formation. The winds that are blown from massive stars are line-driven, meaning they are accelerated by the pressure of the star's radiation on the absorption lines of the heavy elements in the star's atmosphere. A metal-free star, therefore, would have a much weaker wind than a metal-rich star. The supernova explosions of the first metal-free stars are also thought to have been much more energetic than those of modern metal-rich stars. This means that the feedback from the first generation of stars and galaxies would have been very different from the feedback we see today. The story of reionization is therefore not just a story of ionization. It is also a story of chemical enrichment, a story of the complex and beautiful interplay between the radiative, the chemical, and the mechanical feedback from the first stars and galaxies. A story that set the stage for all the subsequent and ever more metal-rich evolution of our cosmic home. The first galaxies to form in the universe, the faint, distant objects that were the protagonists of the epoch of reionization, were very different beasts from the grand, majestic galaxies that we see in the local universe today. They were smaller, they were messier, they were more active, and they were, in a very real sense, the pioneers of the cosmos, the entities that first brought light and complexity to a dark and simple universe. Our current picture of these first galaxies is a composite one, built from the deep images of the Hubble and Webb Space Telescopes, and from the detailed predictions of our cosmological simulations. They are thought to have been much smaller and less massive than modern galaxies, with masses of perhaps only 1 million to 1 billion times that of the Sun, compared to the trillion solar masses of a galaxy like our own Milky Way. They would have been much more numerous, the small building blocks of the later, larger galaxies in the hierarchical model of structure formation. Their shapes would have been much more irregular and clumpy than the beautiful, spiral, and elliptical morphologies of modern galaxies. They were still in the process of being assembled. Their structures shaped by the chaotic accretion of gas from the cosmic web and by the frequent mergers with other small galaxies. But what they lacked in size and elegance, they made up for in vigor. The first galaxies are thought to have been incredibly active sites of star formation. Their star formation rates, the amount of gas they were converting into stars per year, are thought to have been much higher per unit mass than in modern galaxies. This is because they were sitting at the nodes of the cosmic web, with a rich and continuous supply of cold, primordial gas flowing into them. This intense and often bursty star formation was what powered the epoch of reionization. And the stars that were being formed in these first galaxies were also different. The low metallicity of the gas would have favored the formation of more massive, hotter, and shorter-lived stars than in the modern universe. The integrated light from these first galaxies would therefore have had a much harder and more ionizing ultraviolet spectrum. Finally, the environment in which these first galaxies lived was also dramatically different. They were embedded in a dense and mostly neutral intergalactic medium. They had to fight to create their own expanding bubbles of ionization, to burn their way out of the primordial fog, and they were constantly being bombarded by smaller satellite galaxies in a continuous process of mergers and accretion that drove their growth and evolution. As time went on, and as the universe evolved, these first pioneering galaxies would have changed. The process of hierarchical merging would have built them up into larger, more massive, and more structured galaxies. The continued process of star formation and supernova explosions would have gradually enriched them with heavy elements, changing the properties of their stars and their interstellar medium. And the completion of the reionization would have changed their relationship with their environment, from a battle against a neutral fog to a more gentle, symbiotic exchange with a hot, ionized intergalactic medium. The galaxies of today are the mature, evolved descendants of these first, chaotic, and brilliant pioneers. By studying the faint, ancient light from these first galaxies with telescopes like the James Webb Space Telescope, we are not just looking at distant objects. We are looking back in time at our own cosmic ancestors, at the very beginnings of the long, beautiful, and complex story of galactic evolution that has led, eventually, to our own quiet and life-bearing corner of the cosmos. The overlap phase is the critical and most dynamic period of the epoch of reionization. It is the time when the universe was transformed from a state where the ionized regions were isolated bubbles in a sea of neutral gas, to a state where the neutral gas was isolated islands in a sea of ionized plasma. It is the moment of percolation, the point at which the universe became, for the first time since recombination, globally transparent to ionizing radiation. The story begins with the first stars and galaxies carving out their individual, expanding HII regions, or ionized bubbles, in the surrounding neutral intergalactic medium. The size of these bubbles would have depended on the luminosity of the ionizing source and the density of the surrounding gas. In the early stages of reionization, these bubbles would have been small and scattered, concentrated in the densest regions of the cosmic web where the first galaxies had formed. As more and more galaxies turned on, the number and the size of these bubbles would have grown. Eventually, they would have started to touch, to merge, to overlap. This is the beginning of the overlap phase. This process would have been an inside-out one. The densest regions of the universe, the clusters and filaments of the cosmic web, would have been reionized first, as they contained the largest number of ionizing sources. The less dense, void regions would have been reionized later, as the ionizing radiation from the dense regions had to travel across vast distances to reach them. The overlap phase was likely a very rapid and dramatic period of cosmic history. Once the ionized bubbles began to merge, The process would have accelerated, as the ionizing photons could now travel over much larger distances, and the total ionizing background radiation field would have grown exponentially. This would have led to a rapid increase in the global ionization fraction, a rapid heating of the intergalactic medium, and a rapid end to the reionization process. The significance of the overlap phase is profound. It is the moment when the universe's lights truly came on, not just locally, around individual galaxies, but globally. It is the moment that set the stage for the modern, luminous universe we inhabit. And it is a moment that would have left a unique and powerful imprint on our observational probes. The 21-centimeter signal from this era would show a complex and rapidly evolving topology of interconnected, ionized regions and shrinking, neutral islands. The statistics of the Lyman-alpha emitter population would show a rapid increase in the number of visible galaxies, as their Lyman-alpha photons were now able to escape from the increasingly transparent intergalactic medium. The cosmic microwave background would show the characteristic signature of a rapid and relatively late reionization event. The study of the overlap phase is therefore a key goal of modern EOR research. By combining our theoretical simulations with our multi-wavelength observational data, we can hope to create a detailed, four-dimensional movie of this critical and beautifully complex moment in our cosmic history, the moment when the universe was transformed, once and for all, from a dark and opaque place into a luminous and transparent home for all the galaxies and all the life that was to follow. The story of the epoch of reionization, as we currently understand it, is a story that is told in the language of our standard cosmological model, the lambda CDM model. This model, with its 6 key parameters, has been incredibly successful at explaining a vast range of cosmological observations. And when we use this model to simulate the formation of the first stars and galaxies, it predicts a reionization history that is, for the most part, consistent with what we observe. But what if our standard model is incomplete? What if there is new physics beyond lambda CDM? That was at play in the early universe, the epoch of reionization, with its sensitivity to the details of early structure formation, is a powerful and unique probe for searching for the subtle signatures of such new physics. The nature of dark matter, Dushi, for example, is one of the greatest unsolved mysteries in all of science. The cold dark matter of our standard model is assumed to be made of slow-moving, weakly interacting particles. But what if dark matter is not so simple? What if it is warm, made of lighter, faster-moving particles? Warm dark matter would suppress the formation of the smallest dark matter halos, which would delay the formation of the first stars and galaxies, and therefore delay the start of reionization. By using our observations of the EOR to place limits on the number of the first small galaxies, we can place powerful constraints on the mass of a hypothetical warm dark matter particle. What if dark matter can annihilate or decay? This would inject extra energy into the primordial gas, heating it up and partially ionizing it even before the first stars had formed. This pre-reionization would leave a characteristic signature on the 21-centimeter signal and on the polarization of the cosmic microwave background. The nature of the primordial density fluctuations, the seeds of all structure, could also be more complex than in the standard picture, while the lambda CDM model assumes that these fluctuations are almost perfectly Gaussian. Some models of cosmic inflation predict a small amount of non-Gaussianity. This would lead to the earlier formation of rare, massive dark matter halos, which could host the first luminous quasars and could provide an earlier and more patchy start to the reionization process. And finally, the gravitational waves that are predicted to have been generated during the period of cosmic inflation would also leave their mark on the EOR. These primordial gravitational waves would have created subtle, large-scale fluctuations in the density of matter, which would, in turn, have modulated the timing of the formation of the first galaxies and the progress of reionization across the sky. By searching for these large-scale correlations in our future, 3D maps of the 21-centimeter signal, we may be able to detect the faint and long-sought signature of these primordial ripples in the fabric of space-time. The epoch of reionization is a rich and complex astrophysical process, but it is also a pristine cosmological laboratory. It is a place where the subtle and often hidden effects of fundamental physics can be amplified and imprinted onto the large-scale structure of the universe. By studying this crucial era with our new generation of powerful telescopes, we are not just learning about the birth of the first stars and galaxies. We are also opening a new window onto the fundamental laws of nature, a window that may one day reveal the new, and perhaps revolutionary, physics that lies beyond our current standard model. The gravitational waves that ripple through the fabric of space-time, the faint, ancient whispers from the most violent and energetic events in the cosmos, have opened a completely new and revolutionary window onto the universe. And while they are most famously associated with the mergers of black holes and neutron stars in the modern universe, they also have a deep and profound connection to the story of the epoch of reionization, one of the most exciting and also most challenging. Goals of modern cosmology is the detection of the stochastic background of primordial gravitational waves that are predicted to have been generated during the period of cosmic inflation. These are not the sharp chirps from a single cataclysmic event, but a faint, persistent, and random hiss of gravitational waves coming from all directions in the sky, a relic of the quantum fluctuations of space-time itself in the first fraction of a second of the universe's existence. The detection of this primordial background would be a monumental discovery. It would be a direct confirmation of cosmic inflation, and it would give us a glimpse of the universe at energies that are far beyond the reach of any terrestrial particle accelerator. These primordial gravitational waves, as they propagated through the early universe, would have left a subtle imprint on the cosmic microwave background, a specific swirling pattern of polarization known as B-modes. The search for these primordial B-modes is a major focus of current and future CMB experiments, but these same primordial gravitational waves would also have left an imprint on the epoch of reionization. The long wavelength gravitational waves would have created subtle, large-scale fluctuations in the density of matter. These density fluctuations would, in turn, have modulated the timing of the formation of the first galaxies and the progress of reionization across the sky. A region of the universe that was in the trough of a primordial gravitational wave would have a slightly lower density, and reionization would have been slightly delayed. A region in the crest of a wave would have a slightly higher density, and reionization would have been slightly advanced. This would create a large-scale, B-mode-like pattern in our future. 3D maps of the 21-centimeter signal from the epoch of reionization. The detection of this 21-centimeter B-mode signal would be an independent and potentially even more powerful confirmation of inflation than the CMB B-modes. There are other, more astrophysical sources of gravitational waves that are also relevant to the EOR. The mergers of the first stellar mass black holes, the remnants of the first massive population 3 stars, would have produced a background of high-frequency gravitational waves. The future, space-based gravitational wave observatory, LISA, may be sensitive enough to detect this faint cosmic hum. The mergers of the first supermassive black holes in the centers of the first galaxies would have produced a background of much lower frequency gravitational waves, and the very process of the violent, turbulent formation of the first galaxies could have generated a stochastic background of its own. Gravitational waves are a new and powerful tool in our cosmological toolkit. They are a way to probe the universe that is complementary to the traditional electromagnetic observations of light. They allow us to hear the cosmos, to listen to the symphony of space-time itself. And as our gravitational wave observatories become more and more sensitive, they may one day allow us to hear the very first faint notes of that symphony. The primordial whispers from the moment of creation itself, whispers that have been propagating through the cosmos ever since, and which have left their subtle and beautiful imprint on the grand, luminous transformation of the epoch of reionization. The epoch of reionization is not just a crucial chapter in the history of the cosmos. It is also a chapter that has profound implications for one of the oldest and most compelling questions in all of human thought. Are we alone? The EOR is the time when the universe, for the first time, began to be filled with the necessary ingredients and the necessary environments for life as we know it to emerge. The first stars and supernovas, which drove the reionization, also forged and distributed the first heavy elements, the carbon, the oxygen, the nitrogen that are the fundamental building blocks of biochemistry. They created the first habitable zones, the regions around stars where rocky planets could potentially form and where liquid water could exist on their surfaces. The EOR, in a very real sense, is the time when the universe first became habitable. The study of this epoch is therefore crucial for our understanding of the prevalence and the potential distribution of life in the cosmos. By understanding the timeline of the first star formation and the first chemical enrichment, we can begin to estimate when the first potentially life-bearing planets could have formed. Was it possible for life to have emerged in the very early universe, on planets orbiting the first metal-poor population II stars? Or did it have to wait for later generations of stars, like our Sun, to become sufficiently enriched with the heavy elements that are needed for complex chemistry? The properties of the first galaxies also have a direct bearing on their potential habitability. These early, chaotic, and intensely star-forming environments may have been very hostile to life. The high rate of nearby supernova explosions would have bathed any young planets in lethal radiation. The intense ultraviolet flux from the massive, young stars could have stripped away their atmospheres. It is possible that the first truly habitable environments did not emerge until later, in the quieter, more stable suburbs of more mature galaxies like our own Milky Way. But the epoch of reionization also offers a more hopeful perspective. It shows us that the processes that lead to the formation of stars and planets, and the creation of the chemical building blocks of life, are a universal and robust feature of our cosmos. The raw materials for life are not rare, they are ubiquitous. This lends strong support to the cosmic gradualist view of the origin of life. The idea that the emergence of life is not a miraculous, one in a trillion accident, but is the natural, and perhaps even inevitable, outcome of a long and continuous process of cosmic chemical evolution. A process that began in the hearts of the first stars during the epoch of reionization. And finally, our understanding of the EOR has a direct impact on our strategies for the search for extraterrestrial intelligence. If life, and even technological civilizations, could have emerged much earlier in the universe's history, then the most likely places to look for them may not be in our own, relatively young, Milky Way galaxy, but in the oldest, most metal-rich elliptical galaxies, the ancient cosmic cities that formed and evolved much more rapidly in the early universe. The epoch of reionization is a story that is about much more than just physics and astronomy. It is a story that is about our own cosmic origins. It is a story that is about the conditions that make a universe like ours, a universe that is capable of producing a phenomenon as strange, as beautiful, and as mysterious as life possible. And as we continue to peer back in time to the faint ancient light of this cosmic dawn, we are not just looking for the first stars and galaxies. We are also, in the most profound sense, searching for ourselves. The story of the epoch of reionization is a story that is written in the faint, ancient light from the very edge of the observable universe. But it is a story that is being read, interpreted, and understood here on Earth by a new generation of powerful and technologically advanced observatories. The future of reionization research is a story of these new eyes on the cosmos and of the revolutionary discoveries they are poised to make. The James Webb Space Telescope is, without a doubt, the most powerful tool we have ever built for studying the cosmic dawn. Its large, 6.5-meter, gold-coated mirror and its suite of highly sensitive, infrared instruments are specifically designed to capture the faint, red-shifted light from the very first stars and galaxies. In the coming years, Webb will conduct a series of ultra-deep field observations, peering deeper into the universe than ever before, and pushing our observational frontier back to redshifts of 20 or even higher. It will provide us with the first, statistically significant samples of galaxies from the heart of the EOR, allowing us to measure their luminosity function, their clustering, their star formation rates, and their chemical abundances. It will, for the first time, allow us to directly answer the question of whether the first, faint galaxies were indeed the primary drivers of the reionization process. But Webb will not be alone. A new generation of massive, ground-based optical and infrared telescopes, the 30-meter class extremely large telescopes, are currently under construction. These giants, like the 30-meter telescope in Hawaii and the European Extremely Large Telescope in Chile, will have mirrors that are 5 to 10 times larger than Hubble's, and they will be equipped with sophisticated adaptive optic systems that can correct for the blurring effects of the Earth's atmosphere, giving them a resolution that is even sharper than Webb's. These ELTs will be the perfect follow-up machines for Webb. They will be able to take detailed, high-resolution spectra of the faint, distant galaxies that Webb discovers, allowing us to study their internal dynamics, their chemical composition, and the properties of the gas that is flowing into and out of them. In the radio domain, the Square Kilometre Array, a continent-spanning network of thousands of radio dishes and antennas that will be built in Australia and South Africa, is poised to revolutionize our study of the 21-centimeter signal. The SKA will have a collecting area that is orders of magnitude larger than any existing radio telescope, and it will have the sensitivity and the resolution to create the first true three-dimensional maps of the cosmic web of neutral hydrogen during the epoch of reionization. It will, for the first time, allow us to directly see the ionized bubbles growing and merging around the first galaxies, to create a real-time movie of the reionization process. And in space, a new generation of CMB observatories, like the Japanese Lightbird mission, will map the polarization of the cosmic microwave background with unprecedented sensitivity, searching for the faint, large-scale B-mode signal from cosmic inflation, and providing a new, and even more precise, measurement of the global history of reionization. This is a moment of unprecedented opportunity in the history of cosmology. We are on the verge of a data revolution, a time when our observational capabilities will be so powerful that they will transform our understanding of the cosmic dawn. We are moving from a picture of the epoch of reionization that has been painted in broad, theoretical brushstrokes to one that is being filled in with a rich, vibrant, and beautiful palette of observational detail. The journey is far from over. The universe, as always, will likely have new surprises in store for us, but with these new, powerful eyes on the cosmos, we are poised to write the next, and perhaps the most exciting, chapter in the long and wonderful story of our own cosmic origins. The epoch of reionization is a story that is not just about the past. It is a story that is also about the future. The same dark energy that is now accelerating the expansion of our universe, and that played a subtle but important role in shaping the timeline of the EOR, is also the force that will dictate the ultimate fate of our cosmos. And our study of the EOR is providing us with some of our most powerful clues about the nature of this mysterious and ultimately dominant component of our reality. By precisely measuring the distribution of galaxies and the structure of the cosmic web at the time of the EOR, we can trace the history of cosmic expansion and test whether the properties of dark energy have changed over time. The standard lambda CDM model assumes that dark energy is a cosmological constant, with a constant energy density and an equation of state parameter of exactly -1. But if dark energy is a more dynamic entity, like a quintessence field, then its properties could have evolved over cosmic time. A precise measurement of the baryon acoustic oscillations in the distribution of galaxies at high redshifts is a powerful probe of this. The BO are a relic, standard ruler in the cosmos, a characteristic length scale that was imprinted on the distribution of matter by sound waves propagating in the early universe. By measuring the apparent size of this ruler at different cosmic epochs, we can map out the expansion history of the universe and place powerful constraints on the nature of dark energy. The epoch of reionization is also a crucial anchor point for this story. It is the time when the first large-scale structures were just beginning to form, and their properties are particularly sensitive to the interplay between gravity, dark matter, and dark energy. The James Webb Space Telescope and the new generation of large-scale structure surveys will provide us with the data to perform these precise cosmological tests. But the connection between the EOR and dark energy is not just about using the EOR as a cosmological probe. There is a deeper and more mysterious connection. The vacuum energy of the quantum fields, which is the leading candidate for dark energy, is also thought to have been the driving force behind the period of cosmic inflation that set the stage for the Big Bang and for the EOR itself. It seems that the energy of the void is the protagonist of our entire cosmic story, the force that both initiated our universe in a blaze of inflationary expansion, and the force that is now driving it towards its ultimate accelerating fate. The study of the epoch of reionization is therefore a study of the universe at a critical transitional moment, a moment when the creative, structure-forming power of gravity and dark matter was at its peak, and the universe was just beginning its long, slow handover to the eternal, expansive reign of dark energy. It is a moment that contains the seeds of both our cosmic past and our cosmic future. And as we continue to explore this ancient, distant, and beautiful era, we are not just piecing together the story of our origins, we are also, in a very real sense, reading the first, faint lines of the final chapter of our cosmic destiny. The story of the epoch of reionization is a story of a universe in transformation, a story of the first light, the first stars, and the first galaxies. But it is also a story that is deeply and beautifully human. It is a story of our own insatiable curiosity, of our relentless drive to understand our place in the cosmos, of our ability to build magnificent instruments that can act as extensions of our own senses, allowing us to peer back in time to the very dawn of creation. We are a species that is defined by our questions, and the questions that the epoch of reionization forces us to ask are some of the most profound in all of science. How did the first stars form from the pristine gas of the Big Bang? What was the nature of the feedback that regulated the growth of the first galaxies? What was the interplay between the different sources of ionizing radiation that transformed the universe from a dark, neutral fog into a luminous, transparent cosmos? How did the process of reionization shape the large-scale structure of the universe we see today? And what can this ancient epoch tell us about the fundamental nature of dark matter, of dark energy, and of the very laws of physics themselves? These are the questions that are driving the next generation of cosmological research. And they are questions that we are, for the first time in human history, beginning to have the tools to answer. With the James Webb Space Telescope, with the new, extremely large, ground-based telescopes, with the Square Kilometre Array, with a new generation of CMB observatories, we are entering a true golden age of discovery. The coming decades promise to be a time of profound and perhaps even revolutionary breakthroughs in our understanding of the cosmic dawn. We are like the great explorers of a previous age, setting out on a new ocean, with new maps and new ships, to explore a new, and previously unknown, continent of cosmic time. We do not know what we will find there. The universe, as always, will likely have new surprises, new puzzles, and new wonders in store for us, but the journey itself is a worthy one. It is a journey that connects us to the grand, unfolding story of the cosmos. It is a journey that reminds us of the incredible power of the human mind to comprehend a universe that is so much larger, so much older, and so much stranger than ourselves. And it is a journey that fills us with a deep and abiding sense of awe and wonder. As you lie in the quiet of the night, as your own personal universe of consciousness begins to unfold in the silent theater of your dreams, you can feel a sense of participation in this great human adventure. The very atoms that make up your body were forged in the hearts of stars that lived and died long ago. The consciousness that is now drifting into sleep is a product of a long, unbroken chain of cosmic and biological evolution, a chain that stretches all the way back to the first, faint light of the epoch of reionization. We are not separate from this story. We are a part of it. We are the universe's way of knowing itself. And the quest to understand our origins is the most profound and beautiful expression of that cosmic self-awareness. Take a look at this equation. It is not merely a collection of symbols on a page. It is a whisper from another reality, a reality that underpins our own, a world of shimmering probabilities and ghostly connections. This is the Schrödinger equation, the mathematical heart of quantum mechanics. It does not describe where a particle is, but rather the evolving, wave-like cloud of possibilities of where it could be. It is a map, not of a fixed and solid territory, but of a hidden country of pure potential, a country where the familiar rules of our classical world dissolve into a beautiful and often unsettling strangeness. For decades, this equation was a tool for understanding, for peering into the subatomic realm and making sense of its bizarre behavior. But a new kind of dream has taken hold. A dream not just to understand the universe with this equation, but to build with it, to construct machines that do not just calculate, but that think in the very language of this quantum country. Machines that operate not on the rigid logic of ones and zeros, but on the fluid, superpositional logic of probability itself. These are not just faster computers, they are a new form of computation, a new way of interacting with the fabric of reality. They are a glimpse into how the universe truly works, and perhaps a glimpse into a future where we learn to work with it in ways we are only just beginning to imagine. The genesis of this radical idea can be traced back to the year 1980, to the mind of a physicist named Paul Benioff. In a world where classical computers were just beginning their inexorable march into every corner of our lives, Benioff imagined something fundamentally different. He conceived of a theoretical machine, a quantum Turing machine, that would operate not on the classical bits of information, the simple, binary on or off switches, but on qubits, tiny quantum systems that would obey the strange and wonderful rules of quantum mechanics. At the time, this was an idea that hovered in the borderlands between theoretical physics and science fiction. The practical challenge that gave it urgency was one that was becoming increasingly apparent to physicists: the profound difficulty of simulating the quantum world using classical machines. The problem was not a matter of processing speed, it was a matter of fundamental incompatibility. A classical computer, no matter how powerful, is a creature of certainty. It operates on a linear, step-by-step logic. But the quantum world is a creature of probability, of superposition, of entanglement. To fully simulate even a relatively simple quantum system, a molecule with just a few dozen atoms, for example, would require a classical computer to track an exponentially growing number of possible states. The computational resources required would quickly exceed the number of atoms in the entire observable universe. It was like trying to describe a rich, complex symphony using only the language of a telegraph key, a series of clicks and silences. The information was simply too rich, too multi-layered, to be captured by the limited binary language of the classical world. This fundamental challenge, this computational wall, was recognized independently by two of the great minds of 20th century physics, the Russian mathematician Yuri Manin and the American physicist Richard Feynman. Both arrived at the same radical conclusion. If you want to simulate a quantum system, you need a simulator that is itself quantum. You cannot hope to fully capture the richness of the quantum world using a classical machine. You must build a machine that operates on the same principles, a machine that speaks the same probabilistic language. Feynman, in a now legendary lecture in 1981, articulated this vision with his characteristic clarity and verve. "Nature isn't classical, damn it," he famously declared. "And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy." This was not just a complaint, it was a call to arms, an invitation to a new generation of scientists to think differently about the relationship between computation and the physical world. It was a suggestion that the very laws of physics could be harnessed not just to understand the universe, but to compute with it. The idea of a quantum computer was born, not as a tool for making our existing computers faster, but as a necessary tool for asking deeper questions of nature itself, for building a bridge into the strange and beautiful quantum country that Schrödinger's equation had first mapped out for us. It was a dream of a machine that would be not just a product of human ingenuity, but a true collaborator with the cosmos. In the year 1984, just a few years after Feynman's visionary call to arms, the strange and beautiful principles of the quantum world made their first decisive leap from the esoteric realm of theoretical physics into the practical world of human affairs. This leap was not in the form of a computer, but in something equally revolutionary, a new form of secret keeping. The physicists Charles Henry Bennett and Gilles Brassard, inspired by the deep and often paradoxical nature of quantum measurement, realized that the very fragility of the quantum world, its inherent sensitivity to observation, could be turned into an unbreakable shield for communication. They developed a protocol, now known as quantum key distribution, or QKD, that could create a cryptographic key that was not just computationally difficult to crack, but physically impossible to intercept without being detected. It was a technology that turned the laws of quantum mechanics into the ultimate security guards. To understand the genius of their idea, imagine two people, let's call them Albert and Catherine, who wish to share a secret message. They know that a malevolent eavesdropper, Ella, may be listening in on their communication channel. In classical cryptography, Albert would encrypt his message using a mathematical key, and Catherine would use the same key to decrypt it. The security of this system relies on the secrecy of the key, but if Ella can intercept the key as it is being transmitted, the entire system is compromised. Bennett and Brassard's protocol solves this problem by using quantum mechanics to transmit the key itself. Albert sends Catherine a string of individual photons, the quantum particles of light. Each photon is prepared in a specific quantum state, a state of polarization, which represents a single bit of the secret key, a 0 or a 1. The magic and the security lies in the fundamental act of quantum measurement. If Ella tries to intercept these photons to read the key, she is forced to make a measurement. And as we know from the double-slit experiment, the very act of measuring a quantum system inevitably disturbs it. Her observation will collapse the photon's wave function, altering its polarization state in a subtle but detectable way. After the transmission is complete, Albert and Catherine get on an open public channel and compare a randomly chosen subset of the photons they sent and received. They do not reveal the key itself, only the settings they use to measure the photons. If their results match perfectly, they can be confident that no one has been listening in, and that the remaining undiscussed photons constitute a perfectly secret key that they can then use to encrypt their message using a classical one-time pad cipher. If, however, they find discrepancies in their results, they know that Ella has been eavesdropping. The act of her measurement has left an unavoidable quantum footprint. They can then discard the compromised key and start the process over again. This is a security system of a completely new kind. Its security is not based on the mathematical difficulty of solving a problem, which could one day be broken by a more powerful computer. Its security is guaranteed by the fundamental laws of physics. The universe itself conspires to protect their secret. Any attempt to gain information about the key inevitably creates a disturbance, a trade-off that is hardwired into the very fabric of reality by the uncertainty principle. Bennett and Brassard's work was a watershed moment. It was the first concrete demonstration that the strange and seemingly paradoxical features of the quantum world were not just a source of philosophical debate for physicists, but could be harnessed to create powerful new technologies with real-world applications. It proved that quantum mechanics was not just a descriptive theory, confined to the sterile environment of the laboratory. It was a prescriptive one, a set of rules that could be used to build, to engineer, and to create. Today, quantum key distribution is no longer a theoretical curiosity. It is a rapidly developing technology, with secure quantum communication networks being built and tested around the world. It is being used in sensitive industries, from government and military communications to financial transactions and data centers, to protect our most valuable information from the prying eyes of both present-day hackers and future powerful quantum computers. The story of QKD is a beautiful and powerful example of how a deep theoretical insight into the fundamental nature of reality can lead to a technology that has a profound and lasting impact on our society. It is a testament to the fact that the quest to understand the universe, in all its strangeness and beauty, is not just an intellectual pursuit. It is the very engine of human progress. The unbreakable code of quantum cryptography is not just a technological marvel. It is a philosophical statement, a declaration that in the deep, probabilistic, and observer-dependent reality of the quantum world, some secrets, at least, can be kept forever. The classical computers that power our modern world are, without a doubt, one of the most transformative inventions in human history. They are monuments to our ability to manipulate logic, to control the flow of electrons with exquisite precision, and to build systems of immense complexity. From the intricate simulations that predict our weather to the vast interconnected network of the Internet, from the life-saving diagnostics of medical imaging to the simple act of watching this video, our lives are woven into the very fabric of classical computation. But for all their power, these machines are fundamentally limited. They are creatures of a classical, deterministic world, and they think in a language that is profoundly different from the native language of the universe itself. At their heart, Classical computers process information in bits, tiny, physical switches that can be in one of two definite states, a 0 or a 1, an off or an on. Every calculation, no matter how complex, is ultimately broken down into a long, sequential series of these simple, binary operations. When a classical computer simulates the folding of a protein, it is translating the complex quantum mechanical interactions of thousands of atoms into a vast, but ultimately linear, sequence of ones and zeros. When it renders a photorealistic image in a video game, it is performing a massive number of simple, geometric calculations, one pixel at a time. It is a process of immense speed and precision, but it is fundamentally a process of brute force, of solving a problem by marching through all the possible steps, one by one. This approach works remarkably well for a vast range of problems, but there is a class of problems. A class of problems that often holds the key to our deepest scientific and technological challenges, where this linear, step-by-step approach fails catastrophically. These are problems whose complexity grows exponentially with the size of the system. The simulation of a quantum molecule is a prime example. For each new electron you add to the simulation, the number of possible quantum states that the system can be in doubles. The complexity of the problem explodes. For these kinds of problems, even the most powerful supercomputer on Earth is like an abacus trying to calculate the trajectory of a rocket to Mars. It is not just a matter of making the computer faster. The problem itself is of a different order of complexity. It is a problem that requires a different kind of thinking. Quantum computers are not just a faster version of classical computers, they are a fundamentally new kind of machine, a machine that thinks in a fundamentally new way. They are designed to speak the native, probabilistic language of the quantum world. They process information not in bits, but in qubits. A qubit is not a simple on or off switch. It is a tiny quantum system, an atom, an ion, a photon, a superconducting circuit that can exist, thanks to the principle of superposition, in a combination of both 0 and 1 at the same time. It is not either 0 or 1. It is a weighted blend of both. This single, simple difference is the source of all of a quantum computer's power, because a qubit can be both 0 and 1 simultaneously. A quantum computer with just a few qubits can explore a vast computational space. In a single step, a 2-qubit system can be in a superposition of 4 states. A 3-qubit system can be in 8 states. The number of states grows exponentially. A quantum computer with just 300 qubits could, in principle, represent more possible states simultaneously than there are atoms in the entire observable universe. This is a computational space of truly cosmic proportions. To understand the power this gives, imagine trying to find your way through a vast, complex maze with a single, correct path. A classical computer is like a person walking through the maze, trying each path one by one, hitting a dead end, backtracking, and trying another. It is a slow, painstaking, sequential process. A quantum computer, on the other hand, is like a flood of water that is poured into the maze. The water flows down all possible paths simultaneously. By observing where the water comes out, you can instantly determine the correct path. This is the power of quantum parallelism, the ability to perform a massive number of calculations at the same time. But the magic of quantum computing does not stop with superposition. It also harnesses the strange and powerful phenomenon of entanglement. When qubits become entangled, their fates become linked, no matter how far apart they are. The state of one qubit instantly influences the state of another. This creates a deep, non-local connectivity within the quantum computer, allowing for complex correlations and information processing that are impossible in a classical machine. It is as if the different parts of the computation are in constant, instantaneous communication with each other, sharing information and working together in a holistic, coordinated way. It is this combination of superposition and entanglement that gives quantum computers their potential to solve certain specific classes of problems that are intractable for any classical computer. These are not everyday problems, like sending an email or streaming a video. They are the deep, hard problems at the frontiers of science and technology, simulating the behavior of new molecules for drug discovery and materials science. Solving complex optimization problems in logistics and finance, and, most famously, breaking the cryptographic codes that protect our digital world. A quantum computer is not a universal problem solver, but for the right kind of problem, it is a tool of almost unimaginable power, a tool that allows us to tap into the vast, hidden computational resources of the quantum realm itself. The potential of quantum computers to revolutionize our world is perhaps most starkly illustrated in the field of cryptography. Our modern digital economy, from online banking and e-commerce to secure government communications, is built on a foundation of public key cryptography, most famously the RSA algorithm. The security of this system relies on a simple but profound mathematical asymmetry. It is very easy to take two large prime numbers and multiply them together, but it is incredibly computationally difficult to take their large product and find the original two prime factors. A classical computer, even a supercomputer, would have to resort to brute force methods, trying all possible prime factors one by one. For the large numbers used in modern RSA encryption, this process would take a classical computer longer than the age of the universe. This mathematical difficulty is the lock that protects our most sensitive digital information. But in 1994, a mathematician named Peter Shor, then working at Bell Labs, discovered a quantum algorithm that could pick this lock with ease. Shor's algorithm is a beautiful and ingenious piece of mathematics that shows how a quantum computer could find the prime factors of a large number exponentially faster than any known classical algorithm. It does this by cleverly using the principles of quantum parallelism and interference. A quantum computer running Shor's algorithm can, in a sense, test a vast number of potential factors simultaneously. It then uses a technique called the quantum Fourier transform to create an interference pattern in the probabilities of the different outcomes. A pattern that reveals the period of a certain mathematical function, which in turn allows for the efficient calculation of the prime factors. The details are complex, but the upshot is simple and profound. A sufficiently large and stable quantum computer could break most of the public key cryptography that we rely on today, rendering our current standards of internet security obsolete. This is not a distant, theoretical threat. It is a very real and pressing concern for governments, corporations, and security agencies around the world. The race is now on to develop new, quantum-resistant or post-quantum cryptographic algorithms that are secure against attacks from both classical and quantum computers. This is a fascinating, high-stakes game of cat and mouse, a computational arms race between the code breakers and the code makers. But the power of quantum computing extends far beyond the realm of cryptography. It has the potential to revolutionize a vast range of fields that are currently limited by the computational complexity of the problems they face. In medicine and drug discovery, for example, designing a new drug often involves simulating how a potential drug molecule will interact with a target protein in the body. This is a quantum mechanical problem of immense complexity, and classical computers can only provide rough and often inaccurate approximations. A quantum computer could, in principle, simulate these molecular interactions with perfect accuracy, allowing for the rapid, rational design of new, more effective drugs for a vast range of diseases, from Alzheimer's to cancer. In materials science, a similar logic applies. The properties of a new material, its strength, its conductivity, its magnetism, are determined by the quantum mechanical behavior of its constituent atoms and electrons. A quantum computer could allow us to design new materials from the ground up to create, for example, a room temperature superconductor, a highly efficient catalyst for clean energy production, or a new type of battery with unprecedented energy density. The possibilities are almost limitless. And in the field of optimization, quantum computers could find solutions to some of the most complex logistical problems that plague our modern world. Imagine a quantum algorithm that could optimize the entire global supply chain in real time, reducing waste and increasing efficiency, or one that could solve the traveling salesman problem for a vast network of delivery trucks, finding the most efficient routes and saving immense amounts of time and fuel. Or one that could design new, more efficient financial models for managing risk and optimizing investment portfolios. These are all problems that, in their full complexity, are beyond the reach of classical computers. But they are problems that are perfectly suited to the unique, parallel, and holistic problem-solving capabilities of a quantum computer. The quantum age is still in its infancy, but the promise is clear. We are on the verge of a new computational paradigm, a paradigm that will not just make our computers faster, but will allow us to ask and to answer a new class of questions. Questions that touch on the very foundations of chemistry, of biology, of finance, and of our ability to create a more efficient, more sustainable, and more intelligent world. The promise of quantum computing is so immense, so transformative, that it is easy to get carried away by the hype. It is tempting to see these machines as a kind of technological panacea, a magical solution to all of our most difficult problems. But the reality, as is so often the case in science, is far more nuanced, more challenging, and in many ways, more interesting. Quantum computers are not, and will never be, a universal fix for all of our computational needs. In fact, for the vast majority of the tasks that we use computers for in our everyday lives, they are completely and utterly useless. Checking your email, browsing the web, editing a document, playing a video game. These are all tasks that are perfectly suited to the deterministic, sequential logic of a classical computer. A classical computer excels at executing a long series of simple, well-defined instructions, and it does so with incredible speed and reliability. A quantum computer, on the other hand, is not designed for these kinds of tasks. It is not just that it would be overkill, it would be profoundly impractical. It is like using a delicate, $1 million Formula One racing car to go to the grocery store. It is the wrong tool for the job. The very power of a quantum computer, its ability to exist in a superposition of multiple states, is also the source of its greatest challenges. When you measure the result of a quantum computation, you do not get a single, definite answer. The act of measurement collapses the quantum state, and what you get is a probabilistic outcome. The wave function gives you the probabilities of the different possible answers, but the specific answer you get in any single run of the experiment is fundamentally random. This means that to get a reliable result, you often have to run the same quantum computation many times and build up a statistical distribution of the outcomes. The genius of quantum algorithms, like Shor's algorithm, is that they are cleverly designed to use quantum interference to amplify the probability of the correct answer and to cancel out the probabilities of the wrong answers. But this is a highly non-trivial task, and it is only possible for a very specific class of problems. For most problems, the raw, parallel processing power of a quantum computer is simply lost in a sea of randomness. The second, and perhaps even greater, challenge is the profound fragility of the quantum state itself. The qubits that make up a quantum computer are incredibly, exquisitely sensitive to their environment. They are like tiny, delicate soap bubbles, existing in a fragile state of quantum coherence. Any stray interaction with the outside world, a single photon of light, a tiny vibration, a fluctuation in the ambient magnetic field can act as an unwanted measurement, causing the delicate superposition to collapse in a process called decoherence. When this happens, the quantum information is lost and the computation fails. This is the great enemy of quantum computing. To protect their qubits from decoherence, quantum computers must be built and operated under the most extreme conditions imaginable. They are housed in complex, multi-layered cryostats that cool them down to temperatures just a few millikelvin above absolute zero, colder than the deepest reaches of outer space. They are shielded from all forms of electromagnetic radiation and mechanical vibration. Maintaining these conditions is an immense scientific and engineering challenge. And it is what makes current quantum computers so large, so expensive, and so difficult to scale up. And even with all these precautions, errors are still inevitable. The qubits themselves are not perfect, and the control pulses used to manipulate them are not perfectly precise. This leads to a constant stream of errors that must be corrected. The theory of quantum error correction is a beautiful and sophisticated field of research, but it comes at a very high price. To create a single, stable, logical qubit that is protected from errors, you need to use a large number of physical qubits, perhaps hundreds or even thousands, to encode the information in a redundant way and to constantly monitor and correct for errors. This means that the number of physical qubits required to build a useful, fault-tolerant quantum computer is far, far greater than the number of logical qubits needed for the computation itself. To run Shor's algorithm to break RSA encryption, for example, might require a few thousand logical qubits, but with the overhead of error correction, this could translate into a machine with millions of physical qubits. We are currently in an era of noisy intermediate-scale quantum devices, machines with a few dozen to a few hundred physical qubits that are not yet protected by error correction. These are powerful and exciting research tools, but they are a long way from the large-scale, fault-tolerant machines of our dreams. Companies like Google, with its Sycamore processor, and Rigetti, with its Aspen platform, are at the forefront of this research, using their NISQ devices to explore the frontiers of quantum chemistry and machine learning. But the path to a truly universal, fault-tolerant quantum computer is a long and arduous one. And finally, it is important to remember that quantum computers are highly specialized machines. They are not general-purpose computers. They are designed to excel at a very specific set of tasks, those that can exploit the unique properties of quantum mechanics, like factoring and optimization. For a vast range of other problems, a classical computer will always be the faster, more efficient, and more practical tool. The future of computing is not a future where quantum computers replace classical computers. It is a future of hybrid computing, a future where classical and quantum computers work together, each playing to its own strengths. The classical computer will handle the control, the data input and output, and the parts of the problem that are classically easy, and it will hand off the hard quantum part of the problem to the quantum coprocessor. Quantum computers are not the answer to everything, but they are the answer to some of the most profound and important questions we face. They are not tools for making our everyday lives more convenient. They are tools for expanding the very boundaries of human knowledge, for simulating the universe, for discovering new drugs, for creating new materials, and for unlocking the deepest secrets of nature itself. They are not tools for the ordinary, they are tools for the extraordinary. The relationship between the two most transformative and disruptive technologies of our time, quantum computing and artificial intelligence, is a subject of immense interest, speculation, and often confusion. On the one hand, we have the strange, probabilistic, and mind-bending world of quantum mechanics, a world that even its founders famously claimed not to understand. If you are not shocked when you first come across quantum mechanics, Niels Bohr is reputed to have said, "You cannot possibly have understood it." Erwin Schrödinger, whose equation is the very bedrock of the theory, once lamented, "I do not like it, and I am sorry I ever had anything to do with it." This is a theory that challenges our deepest intuitions about reality. And yet, from this strange and unsettling foundation, we are now building machines of almost unimaginable power. At the same time, we are witnessing the explosive rise of artificial intelligence, particularly in the form of deep learning. AI is a technology of a very different flavor. It is not built on the strange paradoxes of a fundamental theory, but on the pragmatic and powerful idea of learning from data. An AI system, like DeepMind's AlphaFold, which solved the 50-year-old grand challenge of protein folding, does not work from first principles. It is trained on vast data sets, and it learns to recognize patterns and make predictions with a level of accuracy that can often surpass human experts. AI is fast, it is adaptable, and it is surprisingly, and sometimes unsettlingly, good at solving problems that we once thought required human intuition. It is natural, then, to ask how these two powerful technologies will interact. Will they be competitors or collaborators? The initial hype around quantum computing often positioned it as the ultimate problem solver, a machine that would render even the most powerful AI systems obsolete. The argument was that many of the hard problems in AI, particularly in machine learning and optimization, are computationally complex, and a quantum computer, with its ability to explore a vast space of possibilities simultaneously, would be the perfect tool to solve them. This has given rise to the field of quantum machine learning, which seeks to develop quantum algorithms that can speed up tasks like classification, clustering, and optimization. But the story, as is so often the case, is more complex. As AI has become more powerful and sophisticated, it has begun to encroach on territory that was once thought to be the exclusive domain of quantum computers. By training on huge data sets of physical simulations, and by incorporating the known laws of physics into their neural network architectures, some AI systems have shown that they can find highly accurate, approximate solutions to complex quantum problems, often much faster and more efficiently than a current, noisy quantum computer could. The CEO of DeepMind, Demis Hassabis, has suggested that for many practical problems in fields like drug discovery and materials science, a clever AI running on a powerful classical computer might be able to find a good enough solution, potentially reducing the need for a full, fault-tolerant quantum computer. This does not mean that quantum computing is a dead end. There are still classes of problems, like factoring large numbers, where a quantum computer is provably exponentially faster than any classical algorithm. But it does suggest that the quantum advantage, the point at which a quantum computer can solve a practical, real-world problem better than any classical computer, may be a more subtle and harder-to-reach target than was once thought. The real story, however, is not one of competition, but of synergy. The future is not about quantum computing versus AI, it is about quantum computing and AI. These are not two competing technologies, but two complementary tools, two different ways of thinking that, when combined, could be far more powerful than either one alone. Imagine a hybrid workflow for discovering a new drug. An AI system could be used to sift through a vast database of millions of potential drug molecules, using its pattern recognition capabilities to identify a few promising candidates. This is a task that AI is perfectly suited for. But then, to truly understand how these candidate molecules will interact with a target protein, to calculate their binding energies with high precision, you need a full quantum mechanical simulation. This is the part of the problem that is classically hard, and it is where a quantum computer would excel. The AI would do the broad, exploratory search, and the quantum computer would do the deep, precise analysis. It is a partnership, a collaboration between two different kinds of intelligence. AI can also play a crucial role in the development of quantum computers themselves. The task of controlling a quantum computer, of calibrating the thousands of delicate control pulses needed to execute a quantum algorithm, is an immensely complex optimization problem. An AI system can be trained to learn the optimal control sequences, to find the best way to tune the machine to minimize errors and maximize performance. In a sense, we are using AI to learn how to speak the language of the quantum world, to find the right words to command our fragile, powerful new machines. This synergy is already being explored in laboratories around the world. Google, for example, with its new Willow quantum chip, is making significant strides in the crucial area of quantum error correction. The Willow chip, with its 105 qubits, is designed to test and improve error-correcting codes, a key step on the road to a fault-tolerant quantum computer. The challenge of error correction is not just about building better hardware. It is also about designing smarter codes and more efficient decoding algorithms. A task where the pattern recognition capabilities of AI could be invaluable. The future, then, is not a simple one of quantum supremacy or AI dominance. It is a more complex and more interesting future of coevolution. Quantum computing provides a new, powerful tool for solving the most difficult computational problems in science, while AI provides a new, powerful tool for learning from data and for controlling complex systems. Together, they are a formidable combination, a partnership that has the potential to accelerate the pace of scientific discovery and technological innovation in ways that we are only just beginning to comprehend. The story is not about one replacing the other. It is about figuring out where each excels and how they can be woven together to create a computational fabric that is far richer and more powerful than anything we have ever seen before. The idea that the universe itself might be a kind of quantum computer is one of the most profound and mind-bending concepts to emerge from the intersection of physics, computer science, and cosmology. It is a perspective that reframes our entire understanding of reality, suggesting that the cosmos is not just a collection of matter and energy evolving according to physical laws, but is an active, ongoing computation, a process of information being transformed and manipulated at the most fundamental level. The physicist Seth Lloyd, one of the pioneers of quantum computing, was one of the first to articulate this idea in a clear and compelling way. He argued that every interaction between elementary particles, every collision, every decay, every quantum jump, can be seen as a fundamental computational operation. The universe, in this view, is constantly computing its own future state, moment by moment, through the ceaseless, parallel interactions of all its constituent parts. This is not just a loose metaphor. The principles that govern the universe at its most fundamental level, superposition, entanglement, interference, are the very same principles that we are now harnessing to build quantum computers. A quantum computer does not solve problems in the linear, step-by-step fashion of a classical machine. It evolves a quantum state, exploring a vast superposition of possibilities simultaneously, until it settles into a final state that encodes the solution. This is remarkably similar to how the universe itself seems to operate. The wave function of the universe contains a superposition of all possible histories, all possible configurations of matter and energy, and the reality we experience is the result of this universal wave function evolving and collapsing according to the laws of quantum mechanics. It is as if the cosmos is running a massive cosmic program, a program whose output is the reality we observe. This perspective gains a new and tangible significance in light of recent experiments, like the one conducted in late 2022 on Google's Sycamore quantum processor, which simulated the behavior of a traversable wormhole. This was not, of course, the creation of a physical tunnel through space-time, but it was a stunning demonstration of the deep connection between the physics of quantum information and the physics of gravity. The experiment was based on the holographic principle, a profound and counterintuitive idea from string theory and quantum gravity, which proposes that a theory of gravity in a certain number of dimensions can be equivalent to a quantum field theory without gravity in one fewer dimension. It is as if our three-dimensional universe, with all its gravitational complexity, could be a holographic projection of a simpler two-dimensional quantum system living on its boundary. The wormhole simulation on the Sycamore chip was a laboratory test of this ADS-CFT correspondence, as it is technically known. The researchers created a highly entangled state of a few qubits on their quantum processor, a state that was mathematically equivalent via the holographic duality to a simplified model of two black holes connected by a wormhole. They then dropped a piece of quantum information into one of the black holes on the chip and watched as it scrambled and spread throughout the system, only to re-emerge, perfectly intact, from the other black hole. The information had, in a sense, traversed the simulated wormhole. This was a landmark experiment because it was the first time that a phenomenon with gravitational properties had been observed to emerge from a purely quantum system. It provided a powerful, albeit circumstantial, piece of evidence for the holographic principle and for the deep underlying connection between quantum entanglement and the geometry of space-time. It suggests that the very fabric of our universe, the smooth, continuous space-time of Einstein's gravity, may be an emergent property of the strange, non-local connections of a vast underlying quantum system. Entanglement, in this view, is not just a strange quirk of the quantum world. It is the very thread from which the tapestry of space-time is woven. If the universe is indeed a giant quantum computer, then the implications are staggering. It reframes our entire scientific endeavor. We are not just external observers, discovering the pre-existing laws of a mechanical universe. We are parts of the computation itself, self-aware substructures that are beginning to understand the logic of the program we are running in. The laws of physics are not just a set of external rules, they are the algorithm. And by building quantum computers, we are not just creating powerful new tools. We are, in a very real sense, learning to speak the universe's native language, to write our own subroutines in the cosmic code. The wormhole simulation is just the beginning. In the future, quantum computers could be used to simulate the quantum chaos inside a black hole, to probe the nature of the Big Bang singularity, to understand the properties of dark matter, or to explore the landscape of possible universes predicted by string theory. They could become our ultimate tool for exploring the frontiers of fundamental physics, a way to create and study toy universes in the laboratory, to test our most ambitious and speculative ideas about the nature of reality. This perspective also offers a new way to think about the complexity of the universe. The sheer, overwhelming complexity of a biological organism, of an ecosystem, of a conscious brain, can seem almost miraculous, almost impossible to have arisen from simple, random processes. But if the universe is a quantum computer, then it is a complexity-generating machine of almost infinite power. The parallel processing capabilities of the cosmos are constantly exploring a vast space of possibilities. And the emergence of complex and ordered structures may be a natural and even inevitable outcome of this cosmic computation. But this grand vision must be tempered with a dose of humility. A humility that comes from confronting the true, unimaginable scale of cosmic complexity. The notion that we could one day build a quantum computer that could simulate the entire universe is a form of computational hubris. The universe is, by definition, the most powerful computer it is possible to build for simulating itself. Any computer we build within the universe will, of necessity, be a smaller, and therefore less powerful, part of the whole. The wormhole experiment on the Sycamore chip did not simulate a real astrophysical wormhole. It simulated a highly simplified toy model, a model that was specifically designed to be simple enough to run on a few noisy qubits. This is a crucial point, and it brings us to a deep and often overlooked aspect of the relationship between computation, complexity, and our own human cognition. The universe may be a quantum computer of infinite capacity, but our own minds, and the computers we build as extensions of our minds, are finite. We are, and will always be, dealing with a sliver of reality, a manageable approximation of an infinitely complex whole. The universe, in its raw, untamed reality, is a place of almost infinite complexity. The number of possible ways that the particles in even a small volume of space can be arranged is a number so vast that it dwarfs any number we have ever encountered in our everyday lives. And yet, we, as human beings, have a powerful, and perhaps necessary, cognitive bias towards simplicity. We are pattern seekers, storytellers. We look for the simple laws, the elegant equations, the coherent narratives that can make sense of this overwhelming complexity. This is the very essence of the scientific endeavor. But in this search for simplicity, we must be careful not to mistake the map for the territory, not to assume that the universe itself is as simple as our models of it. This is a point that is beautifully illustrated by a simple, but profound, thought experiment involving coin flips. If you flip a coin 20 times, the number of possible sequences of heads and tails is 2 to the power of 20, which is just over 1,000,000. The chance of you getting any one specific sequence is 1 in 1,000,000. If you flip the coin 266 times, the number of possible sequences is 2 to the power of 266. A number that is larger than the estimated number of atoms in the entire observable universe. The vast, overwhelming majority of these sequences will look, to our pattern-seeking eyes, completely random, a meaningless jumble of heads and tails, but a few of them will have a simple, recognizable pattern: all heads, all tails, alternating heads and tails. Our minds are immediately drawn to these simple, ordered sequences. We see them as special, as significant, but from a purely probabilistic point of view, the sequence of all heads is just as likely, or rather, just as unlikely, as any other specific, random-looking sequence. Our bias for simplicity is a cognitive illusion. We live in a universe that is, for the most part, irreducibly complex. But our minds are designed to pick out the rare and often illusory islands of simplicity. This has profound implications for how we think about computation, both classical and quantum. A computer, at its core, is a machine for generating sequences of bits, but a classical computer will never, and can never, produce every possible sequence of bits. It is designed to follow a specific, deterministic algorithm, a simple, manageable path through the vast, untamed wilderness of computational possibility. We build our computers to solve the problems that we, with our simplicity-biased minds, have learned how to solve. We keep them on a narrow, well-trodden path because it is the only path we know how to navigate. We often think of computers as being magical, complex machines. But in a deep sense, they are engines of radical simplification. They work because we have forced them to ignore the overwhelming complexity of the real world and to operate in a tightly controlled, logical, and simple sandbox. The same is true, in a different way, for quantum computers. The popular image of a quantum computer is that of a machine that can magically handle an infinite number of variables, a machine that can tame the full complexity of the quantum world. But this is a misconception. A quantum computer does not solve problems by tracking all 2 to the power of 266 possible states of a 266-qubit system. That would be impossible, even for a quantum machine. Instead, a quantum algorithm is a cleverly designed process that uses the principles of superposition and interference to choreograph the evolution of the quantum state in such a way that the vast majority of the computational paths cancel each other out, leaving only the path, or paths, that lead to the correct solution. It is a process of radical quantum mechanical simplification. We are not taming the full complexity of the quantum world. We are finding a clever, simple, and manageable path through it. The problems that quantum computers are good at solving are not the ones that are irreducibly complex, but the ones that have a hidden, simple structure that can be exploited by a quantum algorithm. Factoring large numbers, for example, seems like a hard problem, but it has a hidden, periodic structure that Shor's algorithm is perfectly designed to find. The universe itself may be a quantum computer of infinite complexity, but our own human-made quantum computers will always be tools for finding the pockets of simplicity, the solvable problems that are hidden within that vast cosmic computation. This is not a pessimistic conclusion. It is a realistic one. It is a recognition of our own fundamental cognitive limits, and also of our own unique human genius. Our genius lies not in our ability to comprehend the infinite complexity of the universe, but in our ability to find the simple, beautiful, and meaningful patterns within it. We are the universe's pattern finders, its storytellers, its simplifiers, our science, our art, our technologies. These are all the products of this fundamental human drive to find order in the chaos, to find a signal in the noise. And our most advanced tools, from the James Webb Space Telescope to the next generation of quantum computers, are not tools that will give us a final, complete, and simple answer to the mystery of existence. They are tools that will allow us to ask new, deeper, and more beautiful questions. They are tools that will expand the horizon of our knowledge, and in doing so, will expand the horizon of our wonder. The universe's complexity is not an obstacle to be overcome. It is the very source of its beauty, its mystery, and its endless capacity for novelty. And our own human quest for simplicity is not a flaw. It is the very engine of our own unique and powerful form of understanding.